The universe is often described as vast and mysterious, but what if the key to unlocking its deepest secrets lies not in the grandeur of galaxies, but in the tiniest particles that make up everything we see? Imagine a cosmic tapestry, where the threads of subatomic particles and the colossal structures of galaxies are woven together by an invisible quantum weave. This isn't just science fiction, it's a groundbreaking idea that bridges the gap between the infinitesimally small and the unimaginably large. What if the behavior of particles at the quantum level holds the blueprint for the formation of stars, galaxies, and even the fabric of space itself? Today, we're diving into the science and wonder of this quantum weave, exploring how the rules governing the smallest particles might be the same ones shaping the largest structures in the cosmos. From the strange world of quantum mechanics to the awe-inspiring mysteries of galactic phenomena, this journey will challenge how you see the universe and your place within it. Are you ready to unravel the threads that connect the tiniest particles to the vastness of space? Let's begin. Picture the universe as an intricate spider's web, glistening with dew in the early morning light. Each delicate thread represents a connection between the smallest particles, electrons, quarks, photons, and the vast cosmic structures we see in the night sky. This is the quantum weave, a unifying framework that binds the tiniest bits of matter to the grandest galaxies, challenging the way we think about the cosmos. Unlike traditional physics, which often treats the microscopic and macroscopic worlds as separate realms, the quantum weave suggests they're deeply intertwined, part of a single, interconnected system. Think of it this way: just as a spider's web vibrates when a single strand is touched, the universe might respond in subtle, interconnected ways when particles interact on the quantum level. These interactions could ripple outward, influencing the formation of stars, the behavior of black holes, and even the expansion of space itself. It's a radical idea that blurs the lines between quantum mechanics and astrophysics, suggesting that the rules governing the smallest scales might also shape the largest structures we observe. But why does this matter? Understanding the quantum weave could unlock answers to some of the most profound questions in science. How did the universe begin? What is the true nature of dark matter and dark energy? Are space and time as fundamental as we think, or are they emergent properties of something deeper? By exploring this cosmic tapestry, we're not just studying the universe, we're redefining what it means to explore it. This concept didn't emerge overnight. It's the result of decades of research, experimentation, and bold thinking by scientists who dared to look beyond the boundaries of their fields. So, where did this idea of a quantum weave come from, and how did it evolve into a framework that could revolutionize our understanding of reality? Let's take a closer look at its origins and the brilliant minds who helped weave this cosmic story together. The story of the quantum weave begins not with a single moment of discovery, but with a gradual unraveling of the universe's secrets, a journey that started over a century ago. At the dawn of the 20th century, physicists like Max Planck and Albert Einstein were grappling with phenomena that defied classical physics. Planck's work on blackbody radiation introduced the idea of quantized energy, a revolutionary concept that suggested energy isn't continuous but comes in discrete packets. Einstein took this further with his explanation of the photoelectric effect, showing that light itself behaves as both a particle and a wave. These were the first threads of quantum mechanics, a framework that would forever change how we understand the universe. Niels Bohr added another layer to this tapestry with his model of the atom, where electrons orbit the nucleus in specific energy levels. His insights bridge the gap between the quantum world and the laws governing matter, revealing that even the tiniest particles follow rules that are both precise and profoundly strange. Together, these pioneers laid the foundation for a new way of thinking, one that acknowledged the bizarre, probabilistic nature of the quantum realm. Yet, for all their brilliance, they couldn't have imagined how far these ideas would stretch, or how they might one day connect to the cosmos itself. Fast forward to the modern era, and physicists like Carlo Rovelli and Lee Smolin have taken these early ideas and woven them into a grander vision. Rovelli's work on loop quantum gravity, for instance, proposes that space itself is made up of tiny, discrete loops, a quantum fabric that underlies the smooth spacetime we experience. Smolin, on the other hand, has explored how quantum principles might shape the evolution of the universe, suggesting that time and space emerge from deeper, quantum interactions. These theories don't just connect the dots between quantum mechanics and cosmology. They suggest that the universe is a single, unified system, where the smallest scales and the largest structures are inextricably linked. But what makes the quantum weave so compelling isn't just the boldness of its ideas, it's the mathematical elegance behind them. The equations that describe this framework, from spin networks to quantum fields, paint a picture of a universe that's both dynamic and deeply interconnected. These aren't just abstract concepts. They're tools that allow scientists to explore how particles, forces, and even spacetime itself might emerge from a deeper, quantum reality. It's a vision that challenges us to rethink not just the universe, but the very nature of existence. As we've seen, the quantum weave didn't emerge from a single breakthrough, but from a century of questioning, experimenting, and imagining. It's a testament to the power of human curiosity, and a reminder that the universe's deepest mysteries often reveal themselves slowly, one thread at a time. Now, with this foundation in place, it's time to zoom in even further to the subatomic realm where the quantum weave truly comes alive. What happens when we peer into the heart of matter itself, and how do these tiny particles shape the cosmos we see? That's where our journey takes us next. To truly grasp the quantum weave, we need to venture into the subatomic realm, a world so small it defies our everyday intuition. Here, particles like quarks, electrons, and neutrinos play starring roles in the cosmic drama. Quarks, the building blocks of protons and neutrons, are like the invisible architects of matter, while electrons, zipping around atomic nuclei, create the chemical bonds that shape everything from water to DNA. And then there are neutrinos, ghostly particles that pass through matter almost unnoticed, yet they are so abundant that trillions stream through your body every second. These particles are the threads of the quantum weave, each one following rules that seem almost magical in their precision, but particles don't exist in isolation. They're governed by four fundamental forces that dictate how they interact. Gravity, the force that keeps planets in orbit and galaxies together, is the gentlest of the four, yet its influence stretches across the universe. Electromagnetism, responsible for light, electricity, and magnetism, binds atoms into molecules and powers the technology we rely on every day. Then there's the strong nuclear force, the glue that holds quarks together inside protons and neutrons, and the weak nuclear force, which drives processes like radioactive decay. Together, these forces choreograph a delicate dance of particles, one that shapes the very fabric of reality. Imagine this dance as a cosmic ballet, where each particle moves in perfect harmony with the others, guided by the forces that govern them. Quarks twirl in tight formations, bound by the strong nuclear force, while electrons glide in wider orbits, responding to the push and pull of electromagnetism. Neutrinos, meanwhile, flit through the stage like ethereal dancers, barely interacting with the others but still playing a crucial role in the performance. It's a mesmerizing spectacle, one that reveals the intricate balance of the subatomic world. Recent discoveries have added new layers to this dance. The Higgs boson, often called the God particle, was detected in 2012, confirming a decades-old theory about how particles acquire mass. This discovery was like finding a missing piece of the puzzle, helping us understand why some particles are heavy while others are nearly weightless. It's a reminder that even in the smallest corners of the universe, there are still mysteries waiting to be uncovered. What's truly astonishing is how these tiny particles and forces might influence the largest structures in the cosmos. The same quantum rules that govern the behavior of quarks and electrons could, in some way, shape the formation of galaxies and the expansion of the universe itself. It's as if the subatomic realm and the cosmic scale are two sides of the same coin, connected by the quantum weave, and as we continue to explore this connection, we're not just learning about the universe, we're uncovering the threads that bind it together. So, what happens when we zoom out from the subatomic realm and look at the bigger picture? How do these particles and forces contribute to the grand tapestry of the cosmos? That's where our journey takes us next. Now, let's turn our attention to one of the most mind-bending phenomena in the quantum world, entanglement. Imagine two particles separated by vast distances, perhaps even light years apart, yet somehow they remain intimately connected. If you change the state of one particle, the other instantly responds, as if they're sharing a secret language that transcends space and time. This isn't science fiction, it's quantum entanglement, a phenomenon so strange that even Albert Einstein famously called it spooky action at a distance. But what if this spookiness is more than just a quantum quirk? What if it's a fundamental thread in the cosmic tapestry, weaving the smallest particles into the grandest structures of the universe? To understand entanglement, think of it as a cosmic twin relationship. Two particles, born from the same event or interaction, become so deeply linked that their fates are intertwined. No matter how far apart they drift, their connection remains unbroken. It's as if they're dancing to the same rhythm, even when they are on opposite sides of the universe. This bond isn't just theoretical. It's been proven through experiments like the Bell test, which demonstrated that entangled particles can influence each other instantaneously, defying the speed of light and challenging our understanding of reality itself. The Bell test, named after physicist John Stuart Bell, was designed to settle a long-standing debate about the nature of quantum mechanics. Could particles really be entangled, or was there some hidden variable at play? The results were clear. Entanglement is real, and it's as strange as it sounds. When scientists measured one particle, its entangled partner responded instantly, no matter the distance between them. This discovery didn't just confirm a quantum oddity, it opened the door to a new way of thinking about the universe. If particles can be connected across vast distances, could entanglement be a key piece of the quantum weave, linking the microscopic to the macroscopic? Some theorists suggest that entanglement might play a role in shaping the very structure of the cosmos. Imagine the early universe, a seething cauldron of particles and energy. As particles became entangled, their connections could have laid the groundwork for the formation of galaxies, stars, and even the cosmic web, the vast network of filaments that connects everything in the universe. In this view, entanglement isn't just a curiosity of the quantum world, It's a fundamental force that helps stitch the universe together. But how does this work? One possibility is that entanglement creates a kind of hidden network, an invisible lattice that spans the cosmos. Just as a spider's web connects distant points with delicate threads, entanglement might link particles across unimaginable distances, creating a framework that guides the evolution of the universe. This idea is still speculative, but it's a tantalizing glimpse into how the quantum world might influence the cosmic scale. It suggests that the universe isn't just a collection of separate objects, it's a single, interconnected system, bound together by the strange and mysterious rules of quantum mechanics. As we continue to explore the implications of entanglement, we're not just uncovering the secrets of the quantum realm, we're redefining our understanding of reality itself. Could entanglement be the missing link that connects the smallest particles to the largest structures in the cosmos? It's a question that challenges us to think differently about the universe and our place within it. And as we'll see next, this idea isn't just theoretical. It's already inspiring new ways to explore the quantum weave and its role in shaping the cosmos. One of the most profound ideas in modern physics is that complexity often emerges from simplicity. Take a moment to consider a galaxy, a vast, swirling collection of stars, gas, and dust, stretching across thousands of light years. It's an awe-inspiring structure, but it didn't start out that way. Galaxies, like all large-scale cosmic phenomena, began as something much smaller, tiny fluctuations in the density of matter in the early universe. These fluctuations, driven by quantum effects, grew over billions of years, eventually giving rise to the galaxies we see today. This process of emergence, where simple interactions at the smallest scales lead to complex structures at the largest, is a key part of the quantum weave. But how does this scaling up actually happen? Let's break it down. Imagine the early universe as a simmering pot of particles, each one following the strange rules of quantum mechanics. These particles weren't distributed evenly. Instead, they were clustered in some regions and sparse in others, thanks to tiny quantum fluctuations. Over time, gravity began to pull these denser regions together, causing matter to clump and collapse. As these clumps grew, they formed stars, which gathered into galaxies, and galaxies, in turn, formed clusters and superclusters. What started as a subtle imbalance in the quantum realm became the scaffolding for the entire cosmic structure. This scaling up isn't just about size, it's about the way simple rules can give rise to astonishing complexity. Think of it like a snowflake. A single water molecule is simple, but when countless molecules come together under the right conditions, they create intricate, unique patterns. In the same way, the quantum rules governing particles like entanglement and superposition might influence the behavior of matter on much larger scales. Some scientists even suggest that quantum effects could play a role in galactic formation, shaping the distribution of stars and the rotation of galaxies in ways we're only beginning to understand. Take spiral galaxies, for example. These stunning structures, with their graceful arms of stars and gas, seem to follow a kind of cosmic choreography. But what sets that choreography in motion? One theory is that quantum fluctuations in the early universe left an imprint on the distribution of matter, influencing how galaxies rotate and evolve. It's as if the tiny whispers of the quantum world are still echoing in the vastness of space, shaping the galaxies we see today. But the quantum weave doesn't stop at galaxies. On even larger scales, galaxies themselves come together to form clusters and superclusters, connected by vast filaments of gas and dark matter. These cosmic webs, stretching across billions of light years, are thought to trace back to those same quantum fluctuations in the early universe. In this view, the quantum weave isn't just a metaphor, it's a literal framework that connects the smallest particles to the largest structures in the cosmos. As we explore this scaling process, one thing becomes clear: the universe is far more interconnected than we once thought. The same rules that govern the behavior of quarks and electrons might also shape the evolution of galaxies and the structure of the cosmic web. It's a breathtaking idea, one that challenges us to see the universe not as a collection of separate parts, but as a single, unified system, stitched together by the threads of the quantum weave. Yet, there's still a missing piece to this cosmic puzzle. What about the invisible forces that seem to dominate the universe, dark matter and dark energy? How do they fit into this grand tapestry? That's where our journey takes us next, as we explore the hidden side of the quantum weave and the mysteries that lie just beyond our current understanding. As we've explored the quantum weave, we've seen how the tiniest particles and the grandest cosmic structures are deeply connected. But there's a twist in this cosmic tale, a hidden layer that scientists are still working to unravel. Meet dark matter and dark energy, the universe's most enigmatic players. Together, they make up about 95% of everything in existence, yet we can't see them directly. Dark matter, with its gravitational pull, acts like an invisible glue holding galaxies together, while dark energy pushes the universe to expand faster and faster. These forces are so mysterious that they might hold the key to understanding how the quantum weave operates on a cosmic scale. Let's start with dark matter. Imagine a galaxy spinning like a giant cosmic pinwheel. According to the laws of physics, the outer stars should be flung outward by the galaxy's rotation. But they are not. Something unseen is holding them in place, like an invisible hand guiding the stars in their orbits. That something is dark matter. It doesn't emit light or interact with electromagnetic forces, but its gravitational influence is undeniable. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. Yet, despite its profound impact, we still don't know what dark matter is made of. Could it be composed of exotic particles, like WIMP weakly interacting massive particles, or actions, hypothetical particles born from quantum field theory? The search for answers is one of the most exciting frontiers in modern science. Now, let's turn to dark energy, the force responsible for the universe's accelerating expansion. In the late 1990s, astronomers studying distant supernova made a startling discovery. The universe isn't just expanding, it's speeding up. This unexpected finding pointed to the existence of dark energy, a mysterious force that counteracts gravity on cosmic scales. Unlike dark matter, which pulls things together, dark energy pushes them apart. It's as if the fabric of space itself has an innate energy, causing it to stretch faster over time. But what is dark energy? Is it a property of space, a quantum field, or something entirely different? These questions remain unanswered, but they're driving some of the most ambitious research projects in astrophysics today. What makes dark matter and dark energy particularly intriguing is their potential connection to the quantum weave. Could these hidden forces be manifestations of quantum phenomena on a cosmic scale? Some theories suggest that dark matter particles might interact through quantum fields we haven't yet discovered, while others propose that dark energy could be tied to the quantum vacuum, a sea of energy that permeates all of space. If these ideas hold true, it would mean that the quantum weave isn't just a framework for the visible universe. It's also the foundation for the unseen forces shaping it. Scientists are using a variety of tools to uncover the secrets of dark matter and dark energy. Massive underground detectors are searching for dark matter particles, while telescopes like the James Webb and the upcoming Vera C. Rubin Observatory are mapping the universe's large-scale structure to understand how dark energy influences cosmic evolution. These efforts aren't just about solving a scientific puzzle, they're about peering into the very fabric of reality, uncovering how the quantum weave ties everything together. As we continue to probe these mysteries, one thing becomes clear: the universe is far more complex and far more interconnected than we ever imagined. Dark matter and dark energy aren't just footnotes in the cosmic story, they're central characters, shaping the evolution of galaxies, the expansion of space, and perhaps even the quantum rules that govern reality. But the story doesn't end here. There's another cosmic player that might hold the key to understanding the quantum weave on an even deeper level: black holes. What role do these enigmatic objects play in the grand tapestry of the universe? That's where our journey takes us next. Now, let's dive into one of the most fascinating and mysterious phenomena in the universe: black holes. These cosmic enigmas aren't just regions of intense gravity. They're like dense knots in the quantum weave, where the rules of gravity and quantum mechanics collide in ways that defy our understanding. Imagine the fabric of space-time as a vast, flowing tapestry. Black holes are the points where that fabric is pulled so tightly that it twists and warps, creating a gravitational pull so strong that not even light can escape. But what happens within these knots, and how do they connect to the quantum weave that binds the universe together? Black holes challenge everything we thought we knew about physics. On one hand, they're governed by Einstein's theory of general relativity, which describes how massive objects warp space-time. On the other, they're deeply tied to quantum mechanics, the realm of probabilities, particles, and uncertainty. This collision of the very large and the very small creates a paradox that scientists have been grappling with for decades. How can something so massive, like a black hole, also be influenced by the tiniest particles and forces? It's a question that pushes the boundaries of our knowledge, and it's one that might hold clues to the true nature of the quantum weave. One of the most groundbreaking discoveries about black holes came from Stephen Hawking, who proposed that they're not entirely black after all. According to Hawking radiation, black holes can emit particles due to quantum effects near their event horizons, the point of no return. Here's how it works. In the quantum realm, pairs of particles and antiparticles constantly pop in and out of existence. Normally, they annihilate each other almost instantly, but near a black hole, one particle can fall in while the other escapes. Over time, this process causes the black hole to lose mass and energy, slowly evaporating. It's a stunning idea that bridges quantum mechanics and gravity, suggesting that even the most extreme objects in the universe are shaped by the rules of the quantum weave. But Hawking radiation isn't the only way black holes connect to the quantum realm. Some scientists speculate that black holes might be more than just cosmic vacuum cleaners. They could be gateways, linking different parts of the quantum weave. Imagine the universe as a vast, interconnected network, with black holes acting as nodes that connect distant regions of space-time. This idea aligns with theories suggesting that black holes might lead to wormholes, hypothetical shortcuts through the fabric of the cosmos. While wormholes remain theoretical, they offer a tantalizing possibility that the quantum weave isn't just a passive framework but an active, dynamic system, with black holes serving as portals or bridges between its threads. The concept of wormholes takes us even deeper into the cosmic tapestry. Picture a tunnel connecting two distant points in space-time, like a hidden passage in the quantum weave. While we haven't observed wormholes directly, their existence is mathematically possible within the framework of general relativity. If they do exist, they could provide a way to traverse vast cosmic distances in an instant, bending the rules of space and time as we know them. But here's the twist: wormholes would likely be unstable, held open by exotic matter with negative energy, a concept that ties back to the quantum realm. It's a reminder that the quantum weave isn't just a static structure. It's a dynamic, ever-changing system, full of possibilities we're only beginning to explore. Black holes and wormholes aren't just scientific curiosities. They're windows into the deepest mysteries of the universe. They challenge us to rethink our understanding of space, time, and reality itself. As we continue to probe these enigmatic objects, we're not just exploring the cosmos, we're unraveling the threads of the quantum weave, one knot at a time. And as we'll see next, this exploration isn't just about understanding the universe. It's about discovering the hidden connections that bind everything together. Imagine holding a piece of paper, flat and smooth. Now, fold it so that two distant points on the paper touch. If you could poke a hole through those points, you'd create a shortcut, a direct path between places that were once far apart. This simple analogy helps us grasp the mind-bending concept of wormholes, hypothetical tunnels through the fabric of space-time that could connect distant parts of the universe. But wormholes aren't just science fiction. They're a serious theoretical possibility, one that could tie the quantum weave to the vastness of the cosmos. Wormholes, also known as Einstein-Rosen bridges, emerge from the equations of general relativity. They're essentially shortcuts through space-time, offering a way to travel vast cosmic distances in an instant. Picture the universe as a vast, intricate tapestry, with wormholes acting as hidden threads that stitch together far-flung regions. These tunnels wouldn't just connect places, they might also link different scales of reality, tying the subatomic world to the galactic. But how could such a thing exist, and what would it take to create or detect one? The formation of a wormhole would require extreme conditions, like the intense gravitational fields found near black holes or the exotic matter with negative energy predicted by quantum theory. This exotic matter, unlike anything we've observed, would be needed to keep the wormhole stable, preventing it from collapsing the moment it forms. Think of it as the cosmic equivalent of scaffolding, propping open a tunnel that would otherwise snap shut. But here's the catch: we don't yet know if this exotic matter exists, or if it's even possible to create. It's one of the many challenges that make wormholes a tantalizing but elusive idea. Detecting a wormhole would be no easier. Unlike black holes, which warp space-time so dramatically that they bend light and distort their surroundings, wormholes might leave only subtle traces. Some scientists suggest that wormholes could create gravitational lensing effects, bending light in ways that could be detected by advanced telescopes. Others propose that wormholes might emit faint signals, like echoes of particles passing through them, but so far, no definitive evidence has been found, leaving wormholes firmly in the realm of theory. If wormholes do exist, their implications would be staggering. They could revolutionize space travel, allowing us to traverse the cosmos in ways that seem impossible today. Imagine sending a probe through a wormhole to explore a distant galaxy, or even using one to communicate across vast interstellar distances. The possibilities are as thrilling as they are speculative. But wormholes aren't just about practical applications. They're also a window into the deeper workings of the universe. They challenge us to think about space and time in new ways, suggesting that the quantum weave might be more dynamic and interconnected than we ever imagined. Yet, wormholes are just one piece of the quantum weave puzzle. They hint at a universe where the smallest particles and the largest structures are deeply connected, but they also raise new questions. How do these cosmic shortcuts fit into the broader framework of the universe? And what other hidden threads might be woven into the fabric of reality? As we continue to explore these mysteries, we're not just uncovering the secrets of wormholes, we're unraveling the threads that bind the cosmos together, one discovery at a time. And with that, we're ready to explore another fascinating aspect of the quantum weave, the role of time itself. How does time fit into this cosmic tapestry, and what does it mean for our understanding of reality? That's where our journey takes us next. What if our universe is just one thread in an endless cosmic tapestry, woven together with countless others? This is the tantalizing idea behind the multiverse theory, a concept that suggests our reality is just one of many, perhaps even an infinite number, of parallel universes. Each of these universes could have its own unique laws of physics, its own history, and even its own version of you. But how does this mind-bending idea connect to the quantum weave we've been exploring? And could the same quantum rules that govern particles in our universe also link us to these alternate realities? Let's unravel this cosmic mystery. The multiverse theory isn't just science fiction. It's a serious scientific idea with roots in both quantum mechanics and cosmology. One version of this theory comes from quantum field theory, which suggests that every possible outcome of a quantum event actually happens, but in separate universes. For example, if a particle has a 50% chance of going left or right, both outcomes occur, but in different realities. These parallel universes branch off from one another, creating a vast, branching tree of possibilities. It's as if the quantum weave isn't just connecting particles within our universe. It's stitching together an infinite number of realities, each one slightly different from the next. String theory, another pillar of modern physics, offers a different perspective on the multiverse. According to this framework, our universe might be just one brain floating in a higher dimensional space alongside countless others. These brains, short for membranes, could exist parallel to one another, separated by dimensions we can't perceive. Occasionally, they might even collide, triggering cosmic events like the Big Bang that gave birth to our universe. In this view, the quantum weave isn't confined to a single universe. It's a multidimensional fabric, connecting realities that exist side by side in ways we can barely imagine. But how do these parallel universes interact, if at all? Some theories suggest that the quantum weave might allow for subtle connections between universes, creating bridges or overlaps. Imagine two pieces of fabric stitched together at the edges. Under the right conditions, threads from one might cross into the other. Similarly, quantum fluctuations or rare events might create temporary links between universes, allowing particles or even information to pass between them. While this idea is still speculative, it opens the door to fascinating possibilities, like the existence of mirror particles or phenomena that bleed through from one reality to another. The multiverse theory also raises profound questions about the nature of existence. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be a universe where gravity is stronger or where time flows backward? And if so, how do these realities coexist within the quantum weave? These questions push the boundaries of our understanding, challenging us to rethink not just the universe, but the very fabric of reality itself. As we explore the multiverse, it's clear that the quantum weave isn't just a framework for our universe. It's a cosmic loom, weaving together infinite realities in ways we're only beginning to understand. Each thread represents a unique universe, with its own story, its own rules, and its own mysteries. Yet amidst this vast tapestry, one question remains: what role do we, as conscious observers, play in shaping the quantum weave? That's where our journey takes us next, as we delve into the fascinating intersection of consciousness and the cosmos. What if the very act of observing the universe changes it? This isn't just a philosophical musing, it's a cornerstone of quantum mechanics, and it brings us to one of the most provocative ideas in modern science: the relationship between consciousness and the quantum weave. The idea that our minds might influence the fabric of reality is as fascinating as it is controversial. Could consciousness be more than just a byproduct of the brain? Could it be a fundamental part of the universe, woven into the same quantum tapestry that connects particles and galaxies? Let's explore this mind-bending possibility. At the heart of this discussion is the observer effect, a phenomenon that reveals just how strange the quantum world can be. In experiments like the double-slit setup, particles behave differently when they're being observed. When no one is looking, they act like waves, spreading out and creating interference patterns. But the moment we measure or observe them, they snap into a single, definite state, as if our awareness forces them to choose a position. This effect suggests that observation isn't passive. It's an active process that shapes reality. But here's the question: does this mean consciousness itself has a role in the quantum weave? Or is it simply the act of measurement that causes the change? This is where theories like Roger Penrose's come into play. Penrose, a renowned physicist, teamed up with anesthesiologist Stuart Hameroff to propose that consciousness arises from quantum processes in the brain. They suggest that microtubules, tiny structures within neurons, could host quantum states that collapse when we make decisions or become aware of something. In this view, consciousness isn't just a product of classical physics, it's a quantum phenomenon deeply tied to the fabric of reality. It's a bold idea, one that blurs the line between mind and matter and challenges us to rethink what it means to be conscious. To grasp the implications of this, let's revisit a classic thought experiment: Schrödinger's cat. In this scenario, a cat in a sealed box is both alive and dead at the same time, thanks to the superposition of quantum states. It's only when we open the box and observe the cat that its fate becomes definite. Some interpretations suggest that it's the act of observation, or even consciousness itself, that collapses the wave function, determining the outcome. But is this really how the universe works, or is it just a metaphor for the strange, probabilistic nature of quantum mechanics? The debate continues, but it highlights the deep connection between observation and reality, and raises profound questions about the role of the observer. What makes this idea so compelling is its potential to bridge the gap between the physical and the metaphysical. If consciousness is woven into the quantum weave, it could mean that our thoughts, perceptions, and even our sense of self are part of a larger cosmic framework. It's a vision that challenges the traditional separation of mind and matter, suggesting that the universe isn't just something we observe, it's something we participate in, shaping and being shaped by the quantum rules that govern it. But let's not get ahead of ourselves. While these ideas are fascinating, they're also highly speculative. The connection between consciousness and quantum mechanics remains one of the most hotly debated topics in science. Critics argue that quantum effects are too delicate to survive in the warm, noisy environment of the brain, while proponents point to emerging evidence that quantum processes might indeed play a role in biological systems. The truth is, we're still in the early stages of exploring this frontier, and the answers may lie in the interplay between physics, biology, and philosophy. As we ponder these questions, one thing becomes clear: the quantum weave isn't just a framework for understanding the universe, it's a lens through which we might begin to understand ourselves. Could it be that the same threads connecting particles and galaxies also connect us to the cosmos, making consciousness not just a feature of reality, but a fundamental part of it? It's a question that invites us to look inward, even as we gaze outward at the stars. And as we continue to explore the mysteries of the quantum weave, we might just find that the most profound discoveries lie at the intersection of the universe and the mind. So, what's next in this cosmic journey? How do we move from these speculative ideas to concrete understanding? That's where the future of quantum research comes in, a frontier where science and imagination collide, and where the answers might reshape how we see the universe and our place within it. Time has always been one of the most familiar yet mysterious dimensions of our existence. We measure it, we live by it, and yet, when we look closely at the quantum weave, time begins to behave in ways that defy our everyday experience. What if time isn't the steady, unchanging flow we perceive it to be? What if instead, it's deeply intertwined with the quantum realm, shaped by the same rules that govern particles and forces? This is where the quantum weave takes us on another fascinating journey into the nature of time itself. Let's start by imagining time as a river winding its way through the fabric of the universe. In our everyday lives, this river seems to flow in one direction, carrying us from the past to the future. But when we zoom into the quantum scale, the river begins to twist and turn, its currents behaving in ways that challenge our understanding. According to theories like quantum gravity, time isn't a fixed, linear dimension. It's dynamic, malleable, and deeply connected to the quantum weave. In this view, time might ebb and flow, speed up or slow down, depending on the intricate dance of particles and forces. One of the most striking examples of this fluidity is time dilation, a phenomenon predicted by Einstein's theory of relativity. Imagine two clocks, one on Earth and another on a fast-moving spaceship. As the spaceship accelerates, time for the onboard clock slows down relative to the one on Earth. This isn't just a thought experiment. It's been confirmed by precise measurements using atomic clocks on satellites. But what's truly fascinating is how this effect ties into the quantum weave. At the smallest scales, particles don't experience time in the same way we do. They can exist in superpositions, where past, present, and future blur into a single, probabilistic state. It's as if the river of time forks into countless streams, each one representing a different possibility. This idea is at the heart of quantum gravity, a framework that seeks to unify quantum mechanics and general relativity. In this theory, time isn't a background stage on which events unfold. It's an active participant, woven into the fabric of the quantum weave. Some physicists propose that time might emerge from the interactions of quantum particles, like ripples on the surface of a pond. Others suggest that time could be a kind of illusion, a byproduct of our limited perspective as conscious observers. These theories are still in their infancy, but they offer a tantalizing glimpse into how the quantum weave might reshape our understanding of time. Experiments are already shedding light on these ideas. In one groundbreaking study, researchers used entangled particles to explore how time behaves at quantum scales. They found that the order of events, what we think of as cause and effect, can become ambiguous in the quantum realm. In some cases, It's impossible to say which event happened first, as if time itself becomes entangled. This challenges our classical notion of a linear timeline, suggesting that the quantum weave might connect moments in ways we can't yet fully comprehend. So, what does this mean for our perception of past, present, and future? If time is fluid and dynamic, shaped by the quantum weave, then the boundaries between these moments might not be as clear-cut as we think. The past could influence the future in ways that seem paradoxical, and the future might even reach back to shape the present. It's a radical idea, one that invites us to rethink not just the nature of time, but our place within it. As we continue to explore the quantum weave, we're not just uncovering the secrets of particles and forces, we're unraveling the very fabric of time itself. What we discover could redefine how we see the universe, and perhaps even how we see ourselves. And with that, we're ready to explore another layer of this cosmic mystery, the role of information in the quantum weave, and how it might hold the key to understanding the universe's deepest secrets. What if everything we see, touch, and experience, every star, every galaxy, and even our own existence, is nothing more than a projection, a kind of cosmic illusion? This is the startling idea behind the holographic principle, a concept that suggests the universe might be a two-dimensional information screen, like a hologram, with the third dimension we perceive emerging from it. Imagine the quantum weave as a vast, intricate tapestry, but one where the threads aren't just particles and forces, they're bits of information, encoded on a surface we can't see. This isn't just a wild thought experiment, it's a serious scientific theory that could reshape how we understand reality itself. The holographic principle emerged from the study of black holes, those enigmatic knots in the quantum weave where gravity and quantum mechanics collide. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of disorder or information that's proportional to their surface area, not their volume. This was a radical idea because in classical physics, entropy is tied to volume, but Bekenstein's work suggested that all the information about what falls into a black hole is somehow stored on its surface, like data encoded on a cosmic hard drive. This insight led to the holographic principle, which proposes that the entire universe might operate in a similar way, a three-dimensional reality projected from a two-dimensional boundary. It's as if the universe is a hologram, with every particle, every galaxy, and even time itself emerging from a deeper layer of information. To understand this better, think of a holographic image. When you look at a hologram, it appears three-dimensional, but it's actually created by projecting light onto a flat surface. The holographic principle suggests that the universe works in a similar way. What we perceive as three-dimensional space, the stars, planets, and galaxies might be a projection of information encoded on a two-dimensional surface at the edge of the cosmos. This surface isn't something we can see or touch. It's a mathematical boundary, a kind of cosmic canvas where the universe's data is stored. And just as a hologram contains all the information needed to recreate a three-dimensional image, this boundary might contain all the information needed to describe our universe. But how does this connect to the quantum weave? If the universe is a hologram, then every particle, every force, and every interaction is part of a vast informational network. The quantum weave becomes a kind of code, with particles and galaxies as the output of this cosmic computation. It's a vision that blurs the line between physics and information theory, suggesting that the universe isn't just governed by physical laws, it's built from them like a computer running a program. This idea has profound implications for our understanding of reality. If the universe is fundamentally informational, then space, time, and matter might not be the ultimate building blocks of existence. They could be emergent properties arising from something deeper. One of the most intriguing aspects of the holographic principle is how it challenges our notions of scale. In this framework, the smallest particles and the largest structures in the universe are deeply connected, not just through the quantum weave, but through information itself. A single bit of data encoded on the cosmic boundary could influence the behavior of a particle trillions of light years away, as if the universe is a single, unified system. It's a vision that echoes the interconnectedness we've seen throughout the quantum weave, but takes it to a whole new level. As we explore the holographic principle, it's clear that the quantum weave isn't just a framework for understanding particles and forces, it's a lens through which we might begin to see the universe as a whole. From the tiniest quarks to the vast cosmic web, everything is connected, not just by physical interactions, but by the flow of information. It's a breathtaking idea, one that invites us to rethink not just the universe, but our place within it. And with that, we're ready to explore another layer of this cosmic mystery, the role of symmetry in the quantum weave. How do the elegant patterns of symmetry shape the universe, and what do they tell us about the deeper structure of reality? That's where our journey takes us next. Symmetry is often described as nature's hidden language, a universal code that shapes everything from the smallest particles to the grandest galaxies. It's the reason a snowflake looks the same when you rotate it, or why the wings of a butterfly mirror each other perfectly. But symmetry isn't just about beauty or balance. It's a fundamental principle that underpins the very fabric of reality. In the quantum weave, symmetry plays a starring role, governing the behavior of particles and forces, and weaving order into the chaos of the cosmos. So, what exactly is symmetry, and how does it shape the universe we see today? Let's take a closer look. At its core, symmetry is about invariance, the idea that something remains unchanged even when you transform it. In physics, this concept is expressed through symmetries like charge, parity, and time, or CPT for short. Charge symmetry means that the laws of physics don't change if you flip the charges of particles, turning an electron into a positron, for example. Parity symmetry ensures that the universe behaves the same way, whether you're looking at it directly or in a mirror. And time symmetry means that the laws of physics work just as well whether time runs forward or backward. Together, these symmetries form a kind of cosmic rulebook, guiding how particles interact and how forces shape the universe. But symmetry isn't just a passive observer. It's an active participant in the evolution of the cosmos. One of the most dramatic examples of this is symmetry breaking, a process that played a crucial role in the early universe. Picture the universe just moments after the Big Bang, a seething, chaotic soup of energy and particles. At this stage, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, symmetrical force. But as the universe expanded and cooled, this symmetry began to break, like ice cracking under pressure. The forces split apart, each one taking on its own unique identity. This breaking of symmetry didn't just create diversity, it set the stage for the complexity we see today, from the formation of atoms to the birth of galaxies. To understand how symmetry breaking works, think of a ball sitting at the top of a hill. In this state, the system is perfectly symmetrical. The ball could roll in any direction with equal probability. But as soon as the ball starts to roll, the symmetry is broken. The direction it chooses isn't random, it's influenced by tiny fluctuations like quantum vibrations. In the same way, the early universe's symmetry breaking was driven by quantum effects, leading to the rich tapestry of particles and forces we see today. It's a reminder that even the simplest symmetries can give rise to astonishing complexity. Symmetry also plays a key role in unifying the fundamental forces. Physicists have long dreamed of finding a theory of everything, a single framework that explains all the forces of nature. Symmetry is at the heart of this quest. Theories like supersymmetry suggest that every particle we know has a hidden partner, a kind of cosmic twin that could help bridge the gap between quantum mechanics and gravity. While these partners haven't been discovered yet, the idea of symmetry as a unifying principle remains a powerful driving force in physics. It's as if symmetry is the glue that holds the quantum weave together, connecting the smallest particles to the largest structures in the cosmos. Take the strong nuclear force, for example. This force, which binds quarks together inside protons and neutrons, is governed by a symmetry known as SU3. It's a mathematical framework that ensures the force behaves the same way no matter how you rotate or transform the particles involved. This symmetry isn't just a mathematical curiosity, it's the reason matter exists at all. Without it, quarks wouldn't stick together, and protons and neutrons would never form. In this way, symmetry isn't just a feature of the universe, it's the foundation on which everything is built. As we explore the role of symmetry in the quantum weave, it's clear that this principle isn't just a tool for understanding the universe, it's a window into its deepest mysteries. From the breaking of symmetries in the early universe to the elegant patterns that govern particles and forces, symmetry is the hidden order that shapes reality. But symmetry isn't the only force at work in the quantum weave. There's another layer to this cosmic tapestry, one that ties everything together in ways we're only beginning to understand: the concept of emergence. How do simple rules give rise to complex systems, and what does this tell us about the universe as a whole? That's where our journey takes us next. Picture the universe not as a collection of individual particles, but as a vast, shimmering ocean, where every wave and ripple is a particle itself. This is the essence of quantum fields, the invisible fabric that underlies the quantum weave. Instead of thinking of particles as tiny, isolated objects, imagine them as excitations of these fields, like ripples on the surface of a cosmic pond. When a field vibrates, it creates a particle. When it settles, the particle disappears. In this view, the universe isn't made of solid building blocks, it's a symphony of fields, each one playing its part in the grand cosmic orchestra. At the heart of this idea is the Standard Model of particle physics, a framework that describes the fundamental particles and forces that make up the universe. According to the Standard Model, there are fields for every type of particle: an electron field, a quark field, even a Higgs field. These fields permeate all of space, and when they're energized, they produce the particles we observe. Think of it like a musical score. Each field is an instrument, and the particles are the notes it plays. Together, they create the harmony of the quantum weave, a structure that's as elegant as it is complex. But what does it mean for a particle to be an excitation of a field? Let's take the electromagnetic field as an example. This field exists everywhere, even in what we think of as empty space. When this field vibrates, it produces photons, the particles of light. These photons can travel across the universe, carrying energy and information. In the same way, the electron field produces electrons, and the quark field produces quarks. It's a radical way of thinking about matter, one that shifts our focus from individual particles to the fields that give rise to them. The beauty of quantum fields lies in their universality. They're not confined to specific regions of space, they're everywhere, all the time. Even in the deepest vacuum, where no particles exist, the fields are still present, humming with potential energy. This is what physicists call the quantum vacuum, a state that's far from empty. Instead, it's a seething, dynamic sea of fields, constantly fluctuating and giving rise to virtual particles that pop in and out of existence. It's a reminder that the quantum weave isn't just a static structure, it's a living, breathing system full of energy and possibility. One of the most fascinating aspects of quantum fields is how they interact. Just as waves on a pond can interfere with each other, creating patterns of peaks and troughs, quantum fields can overlap and combine, producing new particles and forces. This interplay is what gives rise to the rich diversity of the universe, from the simplest atoms to the most complex molecules. It's also what makes the quantum weave so intricate, with fields weaving together in ways that are both predictable and profoundly strange. But could these fields extend beyond our universe? Some theories suggest that quantum fields might not be limited to the cosmos we can observe. They could stretch into other dimensions or even other universes, creating connections that we can't yet detect. Imagine the quantum weave as a vast, multidimensional tapestry with threads that reach into realms beyond our understanding. It's a tantalizing idea, one that hints at a universe far more interconnected and far more mysterious than we ever imagined. As we explore the concept of quantum fields, it's clear that they're not just a framework for understanding particles and forces, they're the very fabric of reality itself. From the smallest ripples to the largest cosmic structures, everything is connected through this intricate web of fields, and as we continue to unravel their secrets, we're not just learning about the universe, we're discovering the threads that bind it together. But the story doesn't end here. There's another layer to this cosmic tapestry, one that ties everything together in ways we're only beginning to understand: the role of symmetry in the quantum weave. What do these elegant patterns tell us about the deeper structure of reality? That's where our journey takes us next. What if the quantum weave doesn't stop at the edges of our universe? What if it stretches beyond the stars, galaxies, and even the cosmic horizon we can observe, connecting to dimensions or realms we can't yet see? This isn't just a wild speculation, it's a serious scientific possibility, one that takes the idea of the quantum weave to a whole new level. Imagine the universe not as a solitary island, but as part of a vast, interconnected multiverse, where the threads of the quantum weave extend into realms beyond our comprehension. How could this work, and what does it mean for our understanding of reality? To explore this idea, let's turn to string theory, one of the most ambitious frameworks in modern physics. According to string theory, the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in a space with more dimensions than the 3 we're familiar with, up to 10 or even 11 dimensions in some versions of the theory. These extra dimensions aren't just theoretical, they could be the key to understanding how the quantum weave operates on a multiversal scale. Think of it like a musical instrument. Just as a violin string can vibrate in different ways to produce different notes, strings in higher dimensions could create the particles and forces we observe in our universe, and perhaps in others. One of the most intriguing aspects of string theory is the idea of branes, short for membranes. These aren't the kind of membranes you'd find in biology. They're multidimensional surfaces that could exist within the higher dimensional space predicted by string theory. Our universe might be a 3-dimensional brane floating in a higher dimensional bulk, like a sheet of paper suspended in a vast, unseen ocean. Other brains could exist alongside ours, each one hosting its own universe with its own laws of physics. The quantum weave, in this view, might not just connect particles within our universe, it could extend across these brains, linking our reality to others in ways we can't yet detect. But how might these connections work? Imagine two sheets of paper floating parallel to each other. If they're close enough, vibrations on one sheet could influence the other, creating a kind of cosmic resonance. Similarly, quantum interactions on one brain might ripple through the higher dimensional bulk, affecting other brains and their universes. This could explain phenomena that seem mysterious in our universe, like dark energy or the fine-tuning of physical constants. It's as if the quantum weave isn't just a local phenomenon, it's a multidimensional network, stitching together realities we can barely imagine. M-theory, an extension of string theory, takes this idea even further. It proposes that our universe is just one of many in an infinite multiverse, each one existing on its own brane. These universes could be vastly different from ours, with different laws of physics, different histories, and even different forms of life. Yet they might still be connected through the quantum weave, creating a cosmic tapestry that spans not just space and time, but dimensions we can't perceive. It's a vision that challenges us to think bigger than ever before, to see the universe not as a single entity, but as part of an infinitely larger whole. As we explore these ideas, it's clear that the quantum weave isn't just a framework for understanding our universe, it's a bridge to realms beyond it. From the vibrating strings of string theory to the multidimensional brains of M-theory, these theories suggest that the threads of the quantum weave might reach far beyond what we can see, connecting our reality to others in ways we're only beginning to understand. But there's another layer to this cosmic mystery, one that brings us back to the very fabric of space and time, the role of quantum fluctuations in shaping the weave. How do these tiny, unpredictable changes influence the structure of the universe? And beyond, that's where we're headed next. Imagine a vast, silent ocean at night, its surface perfectly still. Now, picture a single drop of water falling into that ocean, creating ripples that spread outward in all directions. These ripples, though small at first, grow and interact, eventually shaping the entire surface of the water. This is the essence of quantum fluctuations, tiny ripples in the fabric of reality that might hold the key to understanding the universe's grand design. These fluctuations, occurring at the smallest scales, could be the threads that vibrate and weave together to create the cosmic tapestry we call the quantum weave. Quantum fluctuations are like the universe's heartbeat, a constant pulse of energy that exists even in the vacuum of space. At the quantum level, particles and energy don't remain perfectly still. Instead, they flicker in and out of existence, creating tiny variations in energy. These fluctuations might seem insignificant, but in the early universe, they were anything but. During the Big Bang, the cosmos was a seething cauldron of energy, and these tiny ripples acted as seeds, planting the first hints of structure in what was once a uniform sea of particles and radiation. Over billions of years, gravity amplified these fluctuations, pulling matter together to form stars, galaxies, and the vast cosmic web that connects everything we see today. To understand how these fluctuations work, think of a guitar string. When you pluck it, the string vibrates, creating sound waves that travel through the air. In the same way, quantum fluctuations can be thought of as vibrations in the quantum fields that permeate the universe. These vibrations aren't random, they follow precise mathematical rules, creating patterns that ripple through space and time. And just as a single plucked string can produce a complex chord, these tiny fluctuations can give rise to the intricate structures we see in the cosmos. The cosmic microwave background, or CMB, is one of the most compelling pieces of evidence for the role of quantum fluctuations in shaping the universe. This faint glow, left over from the Big Bang, is like a snapshot of the early universe, revealing tiny variations in temperature and density. These variations, or anisotropies, are the fingerprints of quantum fluctuations, imprinted on the universe when it was just a fraction of a second old. Over billions of years, these slight differences grew, forming the seeds of galaxies and galaxy clusters. In a sense, the CMB is the universe's baby photo, showing us the first moments of its growth and evolution. But quantum fluctuations aren't just a relic of the past. They are still at work today, shaping the universe in subtle but profound ways. In the quantum vacuum, particles and antiparticles constantly pop in and out of existence, creating a dynamic, ever-changing energy field. This process, known as vacuum energy, might even be responsible for the mysterious force we call dark energy, which is driving the accelerated expansion of the universe. It's as if the quantum weave is still vibrating, its threads stretching and pulling, shaping the cosmos on both the smallest and largest scales. What's truly astonishing is how these tiny fluctuations, occurring at the quantum level, can have such a monumental impact on the universe. They're the building blocks of the quantum weave, the threads that connect the smallest particles to the largest cosmic structures. And as we continue to explore their role, we're not just uncovering the secrets of the universe's past, we're gaining insight into its future. What other mysteries might these fluctuations reveal? How do they fit into the larger picture of the quantum weave? These are the questions that drive us forward, deeper into the cosmic tapestry, where every thread tells a story. And as we peer further into this intricate web, another question emerges. Could these quantum fluctuations also hold the key to understanding the very nature of space and time? That's where our journey takes us next. The early universe was a place of unimaginable energy and chaos, a seething cauldron where the rules of physics as we know them were just beginning to take shape. It's here, in these first moments, that the quantum weave began to weave the cosmic tapestry we see today. Picture the universe not as a vast, empty space, but as a dense, hot soup of particles and energy, all vibrating with the raw potential of existence. This was the stage set by the Big Bang, an event so powerful that it set the entire cosmos into motion. But how did the quantum weave operate in this primordial chaos? And how did it shape the universe we inhabit now? In those first fractions of a second, the universe underwent a period of rapid expansion known as inflation. Think of it like blowing up a balloon at an incredible speed. Space itself stretched, growing exponentially in size. During this time, quantum fluctuations played a pivotal role. These tiny ripples in the fabric of reality, born from the chaotic energy of the early universe, acted as seeds for the structure we see today. They were the first threads of the quantum weave, creating subtle variations in density and temperature. Over billions of years, these fluctuations would grow, pulled together by gravity, to form galaxies, stars, and the vast cosmic web that connects everything in the universe. But the quantum weave didn't just influence the large-scale structure of the cosmos. It also shaped the very building blocks of matter. In the early universe, particles and antiparticles were constantly being created and annihilated, a dance of existence and destruction. For every particle of matter, there was an equal and opposite particle of antimatter. Yet somehow matter won out. This imbalance, known as Baryon asymmetry, is one of the great mysteries of physics. Some theories suggest that quantum effects, like CP violation, a subtle difference in how particles and antiparticles behave, might have tipped the scales in favor of matter. Without this delicate imbalance, the universe as we know it wouldn't exist. As the universe expanded and cooled, the quantum weave continued to shape its evolution. Quarks, the fundamental particles that make up protons and neutrons, began to combine, forming the first atomic nuclei. This process, known as nucleosynthesis, created the lightest elements: hydrogen, helium, and trace amounts of lithium. These elements would later serve as the raw materials for stars and galaxies, the building blocks of everything we see around us. It's a reminder that even the smallest particles are deeply connected to the largest structures in the cosmos, woven together by the quantum weave. One of the most profound insights from the early universe is how quantum effects might have influenced the universe's rapid expansion. Inflation, driven by a mysterious field known as the inflaton, could have been powered by quantum fluctuations. Imagine the inflaton field as a kind of cosmic spring, stretching space with incredible force. Quantum fluctuations in this field would have caused slight variations in the rate of expansion, leading to the density variations we see in the cosmic microwave background today. These variations are the fingerprints of the quantum weave, imprinted on the universe when it was just a fraction of a second old. But the story of the quantum weave doesn't end with the early universe. It continues to shape the cosmos today, influencing everything from the formation of galaxies to the behavior of black holes. And as we look to the future, the quantum weave might hold clues to the universe's ultimate fate. Will the universe continue to expand forever, or will it eventually collapse back in on itself? Could the quantum weave reveal the secrets of dark energy, the mysterious force driving the accelerated expansion of the cosmos? These are the questions that drive us forward, deeper into the cosmic tapestry, where every thread tells a story. As we continue to explore the quantum weave, we're not just uncovering the secrets of the universe's past, we're gaining insight into its future. And with that, we're ready to explore another layer of this cosmic mystery, the role of dark matter and dark energy in shaping the quantum weave. How do these enigmatic forces fit into the grand tapestry of the universe? That's where our journey takes us next. What lies at the end of the cosmic story? Will the universe continue expanding forever, or is there a grand finale waiting in the wings? The fate of the universe is one of the most profound questions in science, and the quantum weave might hold the key to understanding how this cosmic tale will unfold. From the dramatic collapse of a big crunch to the slow fade of heat death, the future of the cosmos depends on the delicate balance of forces and energy forces that are deeply rooted in the quantum realm. Let's explore these possibilities and see how the threads of the quantum weave might shape the universe's ultimate destiny. One possibility is the Big Crunch, a scenario where the universe stops expanding and begins to collapse back in on itself. Imagine the cosmic tapestry we've been exploring stretched to its limits by billions of years of expansion, suddenly starting to unravel. Gravity, the force that binds galaxies and stars together, would eventually overcome the outward push of dark energy, pulling everything back toward a single point. In this scenario, the quantum weave would tighten, its threads converging as the universe contracts. It's a dramatic endgame, one where the universe essentially rewinds itself, collapsing into a state of unimaginable density and heat. But for this to happen, dark energy, the force driving the universe's accelerated expansion, would need to weaken or reverse its effect, something scientists are still trying to understand. On the other end of the spectrum lies the heat death, a far more subtle and gradual end to the cosmos. Here, the universe continues expanding forever, with dark energy dominating over gravity. Picture the cosmic tapestry stretching thinner and thinner, its threads growing faint as the universe grows colder and emptier. Over trillions of years, stars burn out, galaxies drift apart, and even black holes evaporate through processes like Hawking radiation. What's left is a vast, dark expanse where entropy, the measure of disorder, reaches its maximum. In this scenario, the quantum weave doesn't tear or unravel, it simply fades like a tapestry left in the sun too long. The universe becomes a quiet, lifeless void, where even time loses its meaning. Entropy plays a crucial role in both scenarios. Think of it as the cosmic equivalent of wear and tear on a fabric. Over time, even the most intricately woven tapestry will fray and lose its structure. In the universe, entropy increases as energy spreads out and becomes less usable, driving systems toward disorder. The arrow of time, our perception of past, present, and future, is deeply tied to this increase in entropy. It's why we remember the past but not the future, and why the universe evolves from order to chaos rather than the other way around. The quantum weave, with its intricate connections and fluctuations, is no exception. As the universe ages, its threads may stretch, fray, or even dissolve, depending on the balance of forces at play. Dark energy is the wild card in this cosmic card game. Discovered in the late 1990s, this mysterious force is causing the universe to expand faster and faster. Its nature is still one of the greatest mysteries in physics, but its influence on the universe's fate is undeniable. If dark energy remains constant or strengthens over time, the universe is likely headed for heat death. But if it weakens or changes in some unexpected way, other outcomes like the Big Crunch or even a cyclical universe could still be on the table. The quantum weave, with its deep ties to the behavior of particles and fields, might hold clues to how dark energy operates and what its ultimate impact will be. But what does this mean for us, here and now? While these scenarios might seem distant or abstract, they're rooted in the same principles that govern the universe today. The quantum weave isn't just a framework for understanding the past and future. It's a lens through which we can explore the practical applications of physics, from quantum computing to energy technology. And as we'll see next, these applications aren't just about solving cosmic mysteries, they're about shaping the future of humanity. How can we harness the principles of the quantum weave to innovate and thrive in an ever-changing universe? That's where our journey takes us next. The quantum weave isn't just a fascinating concept for understanding the universe. It's also a springboard for technological breakthroughs that could reshape our future. Imagine a world where computers operate not on binary code, but on the strange, probabilistic rules of quantum mechanics. This isn't science fiction. It's the promise of quantum computing, a field that's already making waves in science and industry. By harnessing the principles of the quantum weave, we might unlock computing power far beyond what classical machines can achieve. But how does this work, and what makes quantum computing so revolutionary? At the heart of quantum computing lies the concept of superposition, where a quantum bit or qubit can exist in multiple states at once. Unlike a classical bit, which is either a 0 or a 1, a qubit can be both simultaneously, thanks to the quantum weave's ability to hold multiple possibilities in tension. This allows quantum computers to perform complex calculations at speeds that would take traditional computers millions of years. For example, they could revolutionize fields like cryptography, where breaking codes or designing unbreakable ones requires immense computational power. Quantum cryptography, which uses the principles of quantum entanglement to secure communications, is already being explored as a way to create communication systems that are virtually immune to hacking. Speaking of entanglement, this phenomenon could also pave the way for entirely new forms of communication. Imagine sending information instantaneously across vast distances without the limitations of light speed. While this might sound like teleportation from science fiction, quantum entanglement allows for the transfer of information between particles in a way that defies classical physics. Researchers are already experimenting with quantum teleportation, where the state of one particle is transferred to another, even if they are light years apart. While practical applications are still in their infancy, the potential for secure, instantaneous communication could transform everything from space exploration to global networking. But the quantum weave isn't just about speed and security, it could also revolutionize space travel. One of the biggest challenges in exploring the cosmos is the vast distances involved. With current technology, even reaching the nearest star system would take thousands of years. But what if we could manipulate the quantum weave to create wormholes or harness exotic matter with negative energy? These ideas, once confined to theoretical physics, are now being explored as potential pathways to faster-than-light travel. While the technical hurdles are enormous, the quantum weave offers a tantalizing glimpse of how we might one day traverse the stars. Of course, harnessing the quantum weave isn't without its challenges. Quantum systems are notoriously fragile, requiring extreme conditions like near absolute zero temperatures to function. Even the slightest interference can disrupt delicate quantum states, making practical applications difficult to scale. Moreover, the ethical implications of these technologies are profound. Quantum computing, for instance, could render current encryption methods obsolete, raising questions about privacy and security. And the ability to manipulate quantum entanglement for communication or teleportation could have far-reaching consequences for society, from military applications to the very nature of human connection. As we explore these possibilities, it's clear that the quantum weave isn't just a tool for understanding the universe, it's a catalyst for reimagining our place within it. By unlocking the secrets of the quantum realm, we might not only transform technology, but also gain new insights into the interconnectedness of all things. The quantum weave challenges us to think beyond the boundaries of classical physics, to see the universe not as a collection of separate parts, but as a unified whole. And as we continue to explore its mysteries, we're not just shaping the future of science and technology, we're redefining what it means to be part of a vast, interconnected cosmos. With these possibilities in mind, the quantum weave invites us to consider not just what we can achieve, but how these advancements might inspire new ways of thinking about ourselves and our place in the universe. What does it mean to live in a world where the smallest particles and the largest structures are deeply connected? How might this understanding shape our future, both technologically and philosophically? These are the questions that drive us forward, deeper into the cosmic tapestry, where every thread holds the potential for discovery. The quantum weave doesn't just challenge our understanding of the universe, it shakes the very foundations of how we perceive reality itself. Think about it. If the tiniest particles are entangled across vast distances, and if the act of observation can fundamentally alter their behavior, what does that say about the nature of existence? It's a question that bridges science and philosophy, inviting us to rethink everything we thought we knew about space, time, and even causality. The quantum weave isn't just a scientific framework, It's a lens through which we can examine the deepest questions of reality. Take the double-slit experiment, a cornerstone of quantum mechanics. When particles like electrons are fired through two slits, they don't behave like tiny bullets following predictable paths. Instead, they act like waves, creating an interference pattern on a detector screen. But here's where it gets strange. If you try to observe which slit the electron goes through, the interference pattern disappears. The particle chooses to behave differently simply because it's being watched. This experiment isn't just a curiosity, it's a profound statement about the nature of reality. It suggests that the universe isn't a fixed, objective entity, but something that responds to observation, a dynamic interplay between the observer and the observed. This idea has radical implications for how we think about causality, the relationship between cause and effect. In classical physics, events unfold in a linear, predictable sequence. A cause is B, which causes C, and so on. But in the quantum realm, this neat chain of causality breaks down. Particles can exist in multiple states at once, and the act of measurement seems to collapse these possibilities into a single outcome. It's as if the universe is constantly rewriting its script, with observation as the pen. This challenges our traditional notions of time and sequence, suggesting that the past, present, and future might be more fluid than we think. The quantum weave also invites us to reconsider the concept of space. If particles can be entangled across vast distances, instantaneously influencing each other, then space might not be the fixed, empty backdrop we imagine. Instead, it could be a dynamic, interconnected field, where distance is less about physical separation and more about the relationships between things. This view aligns with theories like loop quantum gravity, which propose that space itself is woven from discrete, quantized threads. In this framework, space isn't a passive stage, it's an active participant in the cosmic dance. But the philosophical implications don't stop there. The quantum weave also raises questions about the nature of existence. If reality is shaped by observation, does that mean consciousness plays a fundamental role in the universe? Some theorists, like those behind the Orch model, suggest that quantum processes in the brain might give rise to consciousness itself. It's a bold idea, one that blurs the line between mind and matter, and suggests that the universe might be more like a vast, interconnected mind than a collection of inert objects. This shift in perspective has the potential to inspire new paradigms in both science and philosophy. The quantum weave challenges us to move beyond reductionism, the idea that everything can be understood by breaking it down into smaller parts, and toward a more holistic view of reality. It suggests that the universe isn't just a collection of separate entities, but a unified whole, where every part is connected to every other part. This idea resonates with ancient philosophical traditions, from Eastern philosophies that emphasize interconnectedness to indigenous worldviews that see all life as part of a single web. And the implications don't end with science and philosophy. The quantum weave could also have profound cultural and artistic significance. Imagine a world where the boundaries between observer and observed, between self and other, begin to dissolve. Artists might draw inspiration from the idea that reality is a collaborative act, shaped by perception and interaction. Writers could explore stories where time and space are fluid, where characters navigate a universe that responds to their thoughts and choices. The quantum weave offers a new way of seeing the world, one that's rich with possibility and ripe for creative exploration. As we reflect on these ideas, it's clear that the quantum weave isn't just a scientific concept, it's a gateway to reimagining reality itself. From the nature of existence to the role of consciousness, It challenges us to think differently about the universe and our place within it. And as we'll see next, this reimagining isn't just an intellectual exercise. It's a journey that could transform how we live, create, and connect with the world around us. The quantum weave isn't just a playground for scientists. It's also a source of endless inspiration for artists, writers, and musicians who seek to capture the beauty and mystery of the cosmos in their work. Imagine the universe as a vast, cosmic canvas, where the threads of the quantum weave create patterns of light, energy, and motion. This isn't just a metaphor. For many creators, the quantum realm is a muse, sparking ideas that push the boundaries of imagination and expression. From abstract art installations to sweeping symphonies, the quantum weave has become a bridge between science and creativity, offering new ways to explore the profound questions of existence. Take, for example, quantum-inspired art installations that bring the invisible world of particles and fields into the realm of human experience. Artists like Julius von Bismarck and Anneke Ye have used light, sound, and motion to create immersive environments that mimic the behavior of quantum systems. Picture a room filled with shimmering light patterns, where every movement triggers a cascade of reactions, much like particles interacting in a quantum field. These installations don't just visualize science, they evoke the wonder and unpredictability of the quantum world, inviting viewers to feel its rhythms and patterns in a deeply personal way. Literature, too, has been shaped by the quantum weave. Science fiction writers like Philip K. Dick and Ted Chiang have woven quantum concepts into their stories, exploring ideas like parallel universes, entanglement, and the fluid nature of reality. In Chiang's Story of Your Life, the protagonist learns an alien language that changes her perception of time, echoing the non-linear nature of quantum mechanics. These stories don't just entertain, they challenge readers to think differently about the universe and their place within it. By blending science with narrative, authors transform complex ideas into relatable, thought-provoking tales that resonate long after the last page is turned. Music, with its ability to evoke emotion and create connection, has also embraced the quantum weave. Composers like John Adams and Kaija Saariaho have crafted symphonies that mirror the ebb and flow of quantum phenomena. Imagine a piece of music where melodies intertwine like entangled particles, creating harmonies that seem to exist in multiple states at once. These compositions aren't just auditory experiences, they're sonic explorations of the quantum realm, using sound to convey the beauty and complexity of the universe. It's a reminder that science and art aren't separate endeavors, they're two sides of the same coin, each offering unique ways to understand and celebrate the world around us. What makes the quantum weave such a powerful source of inspiration is its ability to make the abstract tangible. Artists and creators translate the strange, counterintuitive world of quantum mechanics into forms that engage our senses and emotions. A painting might capture the duality of light as both particle and wave, while a dance performance could embody the fluidity of quantum states. These works don't just explain science, they invite us to experience it, creating a visceral connection to ideas that might otherwise feel distant or inaccessible. This interplay between art and science has another important role. It makes complex concepts approachable. By blending creativity with scientific insight, artists help demystify the quantum realm, sparking curiosity and wonder in audiences who might never pick up a physics textbook. A sculpture inspired by quantum entanglement, for instance, can spark conversations about the nature of connection, while a science fiction novel might inspire readers to learn more about the real-world theories behind its plot. In this way, art becomes a gateway to science, opening doors to new ways of thinking and seeing the world. As we marvel at the ways the quantum weave has inspired creativity, it's worth asking, how has this interplay between science and art influenced the broader cultural landscape? From blockbuster films to popular music, the quantum weave has left its mark on our collective imagination, shaping how we see the universe and our place within it. But that's a story for the next chapter, where we'll explore the role of the quantum weave in popular culture and how it continues to captivate audiences around the world. The quantum weave isn't just confined to the realms of science and philosophy. It's also woven its way into the stories we tell, the worlds we create, and the games we play. From the silver screen to the pixels of video games, the quantum weave has become a powerful narrative tool, captivating audiences with its blend of mystery, wonder, and endless possibility. Think of it as a cosmic storybook, where the threads of quantum phenomena, entanglement, superposition, and the fluidity of time are spun into tales that stretch the boundaries of imagination. But how exactly has the quantum weave shaped popular culture, and what does it say about our fascination with the unknown? Take Interstellar, for example. Christopher Nolan's epic film doesn't just explore the vastness of space, it delves into the intricate interplay of time, gravity, and human connection. In one unforgettable scene, the protagonist navigates a black hole where time bends and warps in ways that defy our everyday experience. This isn't just science fiction, it's a vivid portrayal of how the quantum weave might operate on a cosmic scale. The film's depiction of higher dimensions and the fluidity of time echoes real scientific theories, like the holographic principle and the nature of space-time. By bringing these ideas to life, Interstellar doesn't just entertain, it sparks curiosity, inviting viewers to ponder the deeper mysteries of the universe. Then there's Doctor Who, a show that has made quantum phenomena a cornerstone of its storytelling. With its iconic TARDIS, a time machine that's bigger on the inside, the series explores the idea of dimensions beyond our perception. The Doctor's adventures often hinge on the quantum weave, from parallel universes to entangled timelines. In one episode, the Doctor encounters a race of beings who exist in multiple dimensions simultaneously, their true forms invisible to human eyes. This portrayal of higher dimensions isn't just a plot device, it's a playful yet profound way to introduce audiences to the strange, counterintuitive world of quantum mechanics. By blending science with whimsy, Doctor Who makes the quantum weave accessible, even for viewers who might not have a background in physics. Video games, too, have embraced the quantum weave as a source of inspiration. No Man's Sky, a game that allows players to explore a procedurally generated universe, is a perfect example. The game's vast, ever-expanding cosmos is a digital reflection of the quantum weave's interconnectedness. Every planet, star, and galaxy is generated through algorithms, creating a universe that feels infinite and dynamic. But what's truly remarkable is how the game captures the sense of wonder and discovery that drives real-world space exploration. By immersing players in a universe where every thread of the quantum weave is a potential adventure, No Man's Sky taps into our innate curiosity about the cosmos. These portrayals of the quantum weave in media aren't just entertainment, they're a bridge between science and storytelling. By weaving quantum concepts into narratives, creators make these complex ideas relatable, sparking interest in science and space exploration. A viewer who's captivated by Interstellar might find themselves reading about black holes or general relativity. A gamer who explores the infinite worlds of No Man's Sky could develop a passion for astronomy or physics. In this way, popular culture becomes a gateway to science, inspiring the next generation of thinkers, explorers, and dreamers. But the impact of the quantum weave on popular culture goes beyond science. It also taps into something deeper, a sense of wonder and spirituality. The idea that everything in the universe is interconnected, from the smallest particles to the largest galaxies, resonates with ancient philosophies and spiritual traditions. Whether it's the Buddhist concept of interdependence or the indigenous belief in the sacred web of life, the quantum weave echoes themes that have fascinated humanity for millennia. In a world that often feels fragmented and divided, the idea of a cosmic tapestry offers a powerful metaphor for unity and connection. As we reflect on the quantum weave's influence on popular culture, it's clear that its appeal lies in its ability to inspire both the mind and the spirit. From the awe-inspiring visuals of Interstellar to the boundless exploration of No Man's Sky, these stories remind us that the universe is a place of endless mystery and possibility. They invite us to look beyond the limits of our understanding and imagine a world where the threads of reality are more intricate and more beautiful than we ever thought possible. And as we continue to explore the quantum weave, we might just find that its threads lead us not only to new discoveries, but also to a deeper sense of connection to each other, to the cosmos, and to the very fabric of existence itself. The quantum weave isn't just a scientific concept, it's a bridge to something much deeper, something that resonates with the very essence of what it means to be human. Across cultures and centuries, humanity has sought to understand the nature of existence, often turning to spirituality for answers. What's fascinating is how many of these spiritual traditions echo the principles of the quantum weave, offering a profound sense of interconnectedness and unity. From the ancient wisdom of Eastern philosophies to the sacred cosmologies of indigenous cultures, the idea that everything is woven together in a cosmic tapestry is a thread that runs through countless beliefs. Could it be that science and spirituality are two sides of the same coin, each offering a unique perspective on the same universal truth? Consider the concept of oneness, a central theme in many spiritual traditions. In Hinduism, the idea of Brahman, the ultimate reality that underlies all existence, reflects a belief in a unified, interconnected universe. Similarly, Buddhism teaches the principle of dependent origination, which holds that all things arise in relation to one another, forming an intricate web of cause and effect. These ideas bear a striking resemblance to the quantum weave, where particles, forces, and even space itself are deeply interconnected. It's as if the spiritual insight of oneness and the scientific understanding of quantum entanglement are pointing toward the same profound truth: that separation is an illusion, and everything is part of a greater whole. Indigenous cosmologies, too, offer a rich tapestry of beliefs that align with the quantum weave. For many indigenous cultures, the natural world is not a collection of separate entities, but a living, interconnected system. The Lakota concept of Mitakui Oyasin, often translated as all my relations, captures this idea beautifully. It speaks to the belief that all life, from the smallest plant to the largest star, is part of a single, sacred web. This worldview mirrors the quantum weave's vision of a universe where every particle, every force, is tied together in a dynamic, ever-changing dance. It's a reminder that the wisdom of ancient traditions might hold keys to understanding the mysteries of the cosmos. But how can the quantum weave bridge the gap between science and spirituality? For centuries, these two realms have often been seen as separate: science focused on the material world, spirituality on the transcendent. Yet, the quantum weave suggests that this divide might not be as clear-cut as we think. When we look at the universe through the lens of quantum mechanics, we see a reality that's fluid, interconnected, and deeply mysterious, qualities that have long been central to spiritual thought. This convergence invites us to see science and spirituality not as opposing forces, but as complementary perspectives, each offering a way to explore the profound questions of existence. Take the concept of consciousness, for example. In many spiritual traditions, consciousness is seen as a fundamental aspect of reality, a force that shapes and is shaped by the universe. This idea finds a surprising parallel in quantum mechanics, where the act of observation seems to play a crucial role in determining the behavior of particles. Could consciousness itself be a thread in the quantum weave, weaving together the observer and the observed in ways we're only beginning to understand? It's a question that blurs the line between science and spirituality, suggesting that the two might be more intertwined than we realize. As we explore these connections, the quantum weave becomes more than just a scientific framework. It becomes a gateway to a deeper understanding of life itself. By weaving together the insights of science and spirituality, we might uncover new ways to see ourselves and our place in the universe. And as we'll see next, this exploration isn't just about understanding the cosmos. It's about discovering what it means to be part of a vast, interconnected whole. Life is one of the most extraordinary phenomena in the universe, but could its origins and evolution be deeply tied to the quantum weave? Imagine the cosmos not just as a vast expanse of stars and galaxies, but as a living, breathing system where the tiniest particles and the grandest structures are all part of a single, interconnected blueprint for life. This isn't just a poetic idea, it's a scientific possibility that challenges how we think about the emergence of life in the universe. From the microscopic interactions of molecules to the cosmic dance of planets and stars, the quantum weave might hold the key to understanding how life begins, evolves, and spreads across the cosmos. One of the most intriguing theories in this space is panspermia, the idea that life isn't confined to a single planet, but could be distributed across the universe through comets, asteroids, or even cosmic dust. But what if the quantum weave plays a role in this process? Picture a cosmic network where particles and energy are entangled across vast distances, creating pathways for life's building blocks to travel. If quantum connections can span the universe, could they also carry the seeds of life from one world to another? It's a radical idea, but one that aligns with the growing evidence that life's ingredients like amino acids and water are surprisingly common in space. To understand how this might work, consider extremophiles, organisms that thrive in Earth's most extreme environments, from scorching hydrothermal vents to the frozen deserts of Antarctica. These resilient life forms show us that life can emerge and persist in conditions once thought impossible. If life can flourish in such harsh environments on Earth, why not elsewhere in the universe? The quantum weave could provide the framework for life to adapt and thrive, even in the most unlikely places. Quantum fluctuations might create the right conditions for chemical reactions to occur, while entanglement could allow life-sustaining energy and information to flow across cosmic distances. But the quantum weave's influence on life might go even deeper. Some scientists speculate that the same quantum processes that govern particles and forces could also play a role in the chemistry of life itself. For example, quantum tunneling, a phenomenon where particles pass through barriers they shouldn't be able to, might be essential for certain biochemical reactions. This could explain how life's complex molecules, like DNA and proteins, form and interact with such precision. In this view, the quantum weave isn't just a backdrop for life, it's an active participant, shaping the very processes that make life possible. The search for extraterrestrial life is another area where the quantum weave could have profound implications. Missions to Mars, Europa, and Enceladus are driven by the hope of finding signs of life. But what if the quantum weave offers new ways to detect it? Imagine a future where we use quantum sensors to detect the faintest traces of life, or where entanglement allows us to communicate with distant civilizations. These possibilities might sound like science fiction, but they are rooted in the same principles that make the quantum weave so fascinating. By exploring these ideas, we're not just searching for life, we're expanding our understanding of how the universe works. As we consider the role of the quantum weave in the origins and evolution of life, it's clear that this cosmic tapestry is more than just a framework for understanding the universe. It's a blueprint for existence itself. From the smallest molecules to the vast reaches of space, the quantum weave connects everything in a dynamic, ever-changing dance. And as we continue to explore its mysteries, we're not just uncovering the secrets of life, we're discovering how deeply intertwined we are with the cosmos. But what happens when we take this exploration a step further? What role could the quantum weave play in the search for extraterrestrial intelligence? That's where our journey takes us next, as we delve into the fascinating intersection of quantum physics and the quest to find other civilizations among the stars. What if the search for extraterrestrial intelligence, or SETI, is not just about scanning the skies for distant radio signals, but about tapping into the very fabric of the universe itself? The quantum weave, with its intricate connections and entangled particles, might offer a revolutionary way to communicate across the cosmos, one that could redefine how we think about finding life beyond Earth. Imagine a civilization so advanced that it doesn't rely on radio waves or lasers to send messages, but instead uses the quantum realm itself as a cosmic telephone line. This isn't just science fiction, it's a tantalizing possibility that could reshape our approach to SETI and our understanding of the universe. Take the WOW signal, for example, a mysterious radio burst detected in 1977 that remains one of the strongest candidates for extraterrestrial communication. For decades, scientists have puzzled over its origin, but what if we've been looking in the wrong place? What if the signal wasn't meant to be detected by traditional radio telescopes, but was instead a quantum-based message, encoded in entangled particles or fluctuations in spacetime? The quantum weave suggests that advanced civilizations might use methods of communication far beyond our current technology, leveraging the strange, instantaneous connections of quantum entanglement to send information across unimaginable distances. In this scenario, the WOW signal might be just one piece of a much larger puzzle, one that requires us to rethink how we search for signs of intelligent life. This idea ties directly into the Drake equation, a formula that estimates the number of active, communicative civilizations in our galaxy. While the equation considers factors like the rate of star formation and the likelihood of planets supporting life, it doesn't account for the possibility of quantum communication. If advanced civilizations are using quantum entanglement to transmit information, our current methods of detection, like radio telescopes, might be missing the mark entirely. The quantum weave could be the missing variable in the Drake equation, a factor that changes the way we calculate the odds of finding extraterrestrial intelligence. By expanding our search to include quantum phenomena, we might unlock a whole new dimension of possibilities, But how could quantum entanglement facilitate communication across the cosmos? Picture two particles separated by light years, yet still connected in a way that defies classical physics. If one particle is altered, the other responds instantly, regardless of the distance. Advanced civilizations could use this phenomenon to create a network of entangled particles, allowing them to send messages faster than the speed of light. This wouldn't just revolutionize communication, it would transform our understanding of time, space, and the limits of technology. The quantum weave, in this context, becomes a cosmic internet, linking civilizations across the galaxy in ways we're only beginning to imagine. Of course, detecting such signals would require technology far beyond what we have today. Traditional SETI efforts focus on electromagnetic signals, but quantum communication might leave no detectable trace in the electromagnetic spectrum. Instead, we'd need to develop new tools capable of sensing subtle quantum effects, like fluctuations in space-time or shifts in entangled particle states. This challenge isn't insurmountable, but it does require a paradigm shift in how we approach the search for extraterrestrial intelligence. The quantum weave invites us to think bigger, to consider not just what we're looking for, but how we're looking. As we explore these possibilities, the quantum weave becomes more than just a scientific framework. It becomes a lens through which we can reimagine our place in the cosmos. By considering the role of quantum phenomena in SETI, we're not just expanding our search for life, we're deepening our understanding of the universe itself. The same principles that govern the behavior of particles might also hold the key to unlocking the mysteries of intelligent life, offering a glimpse into a reality that's far stranger and more interconnected than we ever imagined. But the quantum weave's implications don't stop at communication. What if it also holds the key to understanding the universe's deepest mysteries, from the nature of dark energy to the origins of life itself? As we continue our journey, we'll explore how the quantum weave might illuminate these profound questions, revealing a cosmos that's more dynamic, more mysterious, and more alive than we ever thought possible. The quantum weave isn't just a fascinating framework for understanding the universe. It's a key that could unlock some of the deepest mysteries science has ever faced. From the enigmatic nature of dark matter to the elusive unification of quantum mechanics and gravity, the quantum weave offers a tantalizing path toward answers. But as with any great scientific pursuit, the journey is filled with challenges, questions, and opportunities that push the boundaries of what we know. What are these mysteries, and how might the quantum weave help us solve them? Let's dive in. One of the most pressing questions in modern physics is the nature of dark matter. This invisible substance makes up about 27% of the universe, yet it doesn't interact with light or ordinary matter in any way we can detect. Its presence is inferred only through its gravitational effects, like the way it bends light around galaxies or holds galaxy clusters together. Could the quantum weave hold the key to uncovering dark matter's secrets? Some theories suggest that dark matter particles might interact through quantum fields we haven't yet discovered. If true, this would mean dark matter is deeply woven into the same cosmic tapestry as everything else, connected by the same threads of quantum entanglement and fluctuation. Experiments like the Large Hadron Collider are actively searching for these hypothetical particles, smashing protons together at nearly the speed of light to recreate the conditions of the early universe. While no definitive evidence has been found yet, the search continues, driven by the hope that the quantum weave might reveal what's hidden in the shadows of the cosmos. Another mystery the quantum weave might help solve is the unification of quantum mechanics and gravity. These two pillars of physics describe the universe with remarkable precision, but they operate on entirely different scales and principles. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains the curvature of spacetime caused by massive objects like stars and black holes. Bridging these two frameworks has been one of the greatest challenges in physics, but the quantum weave offers a promising avenue. Theories like loop quantum gravity propose that spacetime itself is made up of tiny, discrete loops, a quantum fabric that underlies the smooth continuum we experience. If proven, this would mean that gravity isn't just a force, it's an emergent property of the quantum weave, a natural consequence of its intricate structure. Testing these theories is no small feat. Unlike particle physics, where experiments like the Large Hadron Collider can recreate extreme conditions, studying the quantum weave requires a different approach. Gravitational wave detectors, like LIGO and Virgo, provide one way to probe these ideas. These instruments detect ripples in spacetime caused by cataclysmic events like black hole collisions, offering a glimpse into the dynamic nature of the universe. By analyzing these waves, scientists hope to uncover clues about how gravity operates at quantum scales. Similarly, experiments with quantum entanglement are pushing the limits of our understanding, revealing connections that defy classical physics. Each discovery brings us closer to unraveling the quantum weave's secrets, but the road ahead is long and filled with unknowns. What makes the quantum weave so revolutionary isn't just its potential to solve existing mysteries, it's its ability to inspire new questions and possibilities. For example, if spacetime is indeed woven from quantum threads, what does that mean for the nature of reality itself? Could the universe be a kind of cosmic computation, with the quantum weave as its underlying code? These ideas might sound like science fiction, but they are grounded in rigorous scientific inquiry. And as we continue to explore the quantum weave, we're not just answering old questions, we're opening doors to entirely new realms of discovery. But the impact of the quantum weave goes beyond science. It's also a source of inspiration for future generations. Imagine a young student captivated by the idea that the universe is a vast, interconnected tapestry. For them, the quantum weave isn't just a theory, it's a call to explore, to question, and to dream. From classrooms to research labs, the quantum weave is sparking curiosity and creativity, reminding us that the universe is full of mysteries waiting to be unraveled. And as we pass this torch of knowledge to the next generation, we're not just sharing science, we're sharing a sense of wonder and possibility. The quantum weave is more than a scientific concept. It's a testament to the power of human curiosity and imagination. From the smallest particles to the grandest cosmic structures, it connects everything in a dynamic, ever-changing dance. And as we continue to explore its mysteries, we're not just uncovering the secrets of the universe, we're discovering what it means to be part of something infinitely greater than ourselves. What new insights will the quantum weave reveal? That's a question only the future can answer. A future shaped by the explorers, thinkers, and dreamers who dare to unravel its threads. And with that, we're ready to explore another layer of this cosmic mystery, the role of the quantum weave in shaping the future of science and exploration. How might this framework inspire the next generation of breakthroughs? That's where our journey takes us next. The quantum weave isn't just a framework for understanding the universe, it's a spark that can ignite curiosity and wonder in the minds of future generations. Imagine a child gazing up at the night sky, not just seeing stars, but envisioning the invisible threads that connect them to the tiniest particles on Earth. This sense of awe and exploration is at the heart of what makes the quantum weave so powerful as a tool for education and inspiration. By making these complex ideas accessible, we're not just teaching science, we're nurturing a lifelong love of discovery. One of the most exciting ways to engage young minds with the quantum weave is through citizen science projects. These initiatives invite people of all ages to participate in real scientific research, from classifying galaxies to tracking quantum fluctuations in data. Take the Zooniverse platform, for example, where volunteers help analyze astronomical images or particle collision data. Projects like these don't just democratize science, they show that everyone, regardless of age or background, can contribute to our understanding of the universe. It's a powerful reminder that science isn't just for experts in labs, it's a shared journey of exploration. STEM education also plays a crucial role in bringing the quantum weave to life. Programs like Quantum Computing for Kids or Physics in a Box use hands-on activities and interactive tools to make abstract concepts tangible. Picture a classroom where students build their own quantum circuits or simulate entangled particles using simple materials. These experiences don't just teach facts, they cultivate creativity, critical thinking, and a sense of wonder. By weaving quantum ideas into the fabric of education, we're equipping the next generation with the tools to tackle the big questions of tomorrow. But inspiring curiosity isn't just about classrooms and experiments, it's about storytelling too. Think of the way documentaries like Cosmos or shows like The Magic School Bus captivate audiences with vivid narratives and relatable analogies. The quantum weave, with its intricate connections and mind-bending phenomena, is a treasure trove of stories waiting to be told. Whether it's the tale of Schrödinger's cat or the mystery of black holes, these stories make science feel alive, sparking imaginations and encouraging young thinkers to ask, what if? Perhaps the most profound impact of the quantum weave is the way it fosters a sense of connection, not just between particles and galaxies, but between people. When we marvel at the universe's interconnectedness, we're reminded that we, too, are part of this cosmic tapestry. This realization can inspire a deeper sense of responsibility, not just for the planet we call home, but for the broader universe we're only beginning to understand. It's a perspective that encourages empathy, collaboration, and a shared commitment to exploring the unknown. As we look to the future, the quantum weave challenges us to think beyond the limits of what we know. It invites us to dream big, to ask bold questions, and to embrace the unknown with curiosity and courage. But with great discoveries come great responsibilities. How do we ensure that our exploration of the quantum weave is guided by ethics and a respect for the interconnectedness of all things? That's where our journey takes us next, as we delve into the ethical considerations of studying the universe's deepest mysteries. As we unravel the mysteries of the quantum weave, we encounter not just scientific challenges, but profound ethical questions. What does it mean to manipulate the very fabric of reality? And how do we ensure that our discoveries are used for the greater good rather than harm? The quantum weave, with its potential to revolutionize technology and deepen our understanding of the universe, also carries a weighty responsibility, one that requires careful thought, collaboration, and ethical foresight. History offers us stark reminders of the dual-use nature of scientific breakthroughs. Take the Manhattan Project, for example. What began as a quest to understand the fundamental forces of nature led to the creation of the atomic bomb, a weapon of unimaginable destruction. Similarly, CRISPR, the gene editing tool, has the potential to cure diseases and improve lives, but it also raises concerns about genetic manipulation and the ethics of altering life itself. These examples serve as cautionary tales, highlighting the need for ethical vigilance as we explore the quantum weave. The same principles that allow us to harness quantum entanglement for communication or energy could also be misused, whether intentionally or unintentionally, with consequences we can't yet fully predict. This dual-use dilemma isn't just about technology, it's about our relationship with the universe itself. The quantum weave challenges us to rethink not just how we manipulate the cosmos, but how we see ourselves within it. Are we merely observers, or do we have a responsibility to act as stewards of the cosmic tapestry? As we gain the ability to influence the quantum realm, we must ask ourselves, what are the limits of our intervention, and how do we balance the pursuit of knowledge with the need to respect the delicate balance of the universe? To navigate these questions, ethical guidelines must be at the forefront of quantum research. This means fostering open dialogue between scientists, ethicists, policymakers, and the public. It means prioritizing transparency and accountability, ensuring that the benefits of quantum discoveries are shared equitably and that potential risks are carefully managed. International collaboration will be key, as the quantum weave knows no borders. Its implications are global, and so too must be our approach to addressing them. By working together, we can create a framework that not only advances science but also safeguards humanity's future. But the ethical considerations of the quantum weave go beyond practical applications. They also touch on the philosophical. If the universe is deeply interconnected, as the quantum weave suggests, what does that mean for our sense of individuality and identity? Are we merely threads in a larger cosmic tapestry, or do we retain some unique essence? These questions challenge us to reflect on our place in the universe, not just as scientists or explorers, but as beings capable of wonder, creativity, and moral reasoning. In this way, the quantum weave isn't just a scientific framework, it's a mirror reflecting back to us the complexities of our own humanity. It invites us to think deeply about the kind of future we want to create, both for ourselves and for the cosmos. And as we continue to explore its mysteries, we must do so with humility, curiosity, and a commitment to the ethical principles that guide us. The quantum weave isn't just a journey of discovery, it's a call to responsibility, reminding us that with great knowledge comes great power, and with great power comes the need for wisdom. With these ethical considerations in mind, we're ready to explore another layer of this cosmic mystery, how the quantum weave might redefine our understanding of humanity's place in the universe. What does it mean to be part of a cosmos where everything is connected, from the smallest particles to the largest galaxies? That's where our journey takes us next. Imagine standing on a mountaintop, gazing at the vast expanse of stars above. For centuries, this view has inspired awe and wonder, but also a profound question: where do we fit into this cosmic picture? The quantum weave offers a revolutionary perspective, one that doesn't just place humanity in the universe, it weaves us into its very fabric. We're not just passive observers of the cosmos, we're active participants, threads in an intricate tapestry that connects everything from the tiniest particles to the grandest galaxies. This isn't just a poetic idea, it's a scientific reality that redefines our understanding of who we are and how we relate to the universe. Think of the universe as a vast, shimmering tapestry, each thread representing a particle, a force, or a cosmic structure. Now, imagine humanity as one of those threads, not isolated, but deeply intertwined with the rest. Every thought we have, every action we take, sends ripples through the quantum weave, influencing the cosmic dance in ways we're only beginning to understand. This interconnectedness isn't just metaphorical, it's rooted in the strange, counterintuitive rules of quantum mechanics. Whether it's the entanglement of particles or the way observation shapes reality, the quantum weave shows us that we're not separate from the universe. We're part of its unfolding story. This perspective challenges the traditional view of humanity as a small, insignificant speck in an indifferent cosmos. Instead, it suggests that we play a meaningful role in the universe's evolution. Consider the double-slit experiment, where the act of observation changes the behavior of particles. This phenomenon isn't just a quirk of quantum mechanics, it's a profound statement about the interplay between observer and observed. In a sense, the universe becomes what we see, and we, in turn, are shaped by what the universe reveals to us. It's a dynamic relationship, one that highlights our active participation in the cosmic process. The quantum weave also invites us to think differently about our connection to each other and the world around us. If everything is interconnected, then the boundaries we often draw between self and other, between humanity and nature, begin to blur. This idea echoes ancient spiritual traditions, from the Buddhist concept of interdependence to the indigenous belief in the sacred web of life. But now, science is giving us a new way to understand these connections, one that's grounded in the behavior of particles and fields. The quantum weave doesn't just unite us with the cosmos, it reminds us that we're part of a larger whole, a single, unified system where every thread matters. This sense of unity has profound implications for how we see our purpose in the universe. If we're woven into the cosmic tapestry, then our actions, no matter how small, have the potential to shape the universe's future. This isn't just about scientific discovery, it's about how we live our lives. The quantum weave inspires us to think beyond our individual concerns and consider the broader impact of our choices. Whether it's advancing technology, protecting the environment, or fostering empathy and connection, we're contributing to the ongoing evolution of the cosmos. As we reflect on humanity's place in the quantum weave, it's clear that this perspective doesn't just change how we see the universe, it changes how we see ourselves. We're not just observers marveling at the stars, we're co-creators, shaping the cosmic story with every thought, every discovery, and every act of kindness. And as we continue to explore the mysteries of the quantum weave, we're not just unraveling the secrets of the universe, we're weaving a future where humanity's role is as vibrant and essential as the stars themselves. But what does this future hold? What new discoveries and breakthroughs will the quantum weave reveal in the years to come? That's where our journey takes us next, as we explore the cutting-edge research and possibilities that lie ahead in the world of quantum physics. The future of quantum weave research is brimming with possibilities, each one promising to push the boundaries of what we know about the universe. Imagine a world where quantum computers solve problems in seconds that would take classical computers millennia, or where space missions uncover secrets hidden in the farthest reaches of the cosmos. These aren't distant dreams, they're the next frontiers of science, and they're closer than you might think. From the cutting-edge tools we're building to the bold collaborations driving innovation, the quantum weave is at the heart of it all, offering a roadmap to discoveries that could redefine reality as we know it. One of the most exciting areas of progress is quantum computing. Unlike traditional computers, which process information in binary bits of zeros and ones, quantum computers use qubits that can exist in multiple states at once, thanks to the principles of superposition and entanglement. This allows them to perform calculations at speeds that are simply unimaginable with today's technology. Already, Companies and research institutions are using quantum computers to tackle problems in fields like drug discovery, materials science, and cryptography. For instance, quantum algorithms are being developed to simulate complex molecular interactions, potentially leading to breakthroughs in medicine and energy storage. But the implications go even further. Quantum computing could help us model the behavior of the universe itself, simulating everything from the formation of galaxies to the intricacies of the quantum weave. Meanwhile, the James Webb Space Telescope is opening new windows into the cosmos, capturing images of distant galaxies and ancient stars with unprecedented clarity. This marvel of engineering isn't just a tool for stunning visuals, it's a gateway to understanding the quantum weave on a cosmic scale. By observing the light from the earliest moments of the universe, scientists can study how quantum fluctuations in the early cosmos shaped the structures we see today. The telescope's ability to peer into the infrared spectrum also allows it to detect the faintest signals from exoplanets, potentially uncovering clues about the origins of life and the role of quantum processes in planetary formation. It's a reminder that the quantum weave isn't just a local phenomenon, it's a universal framework that connects the smallest particles to the largest galaxies. On Earth, quantum simulators are offering another way to explore the quantum weave. These devices mimic the behavior of quantum systems, allowing researchers to study complex interactions that are difficult or impossible to observe directly. For example, scientists are using quantum simulators to investigate the behavior of materials at extreme temperatures or pressures, revealing insights that could lead to new technologies like superconductors or ultra-efficient batteries. These tools are also helping us understand the quantum nature of black holes, wormholes, and other cosmic phenomena, bridging the gap between the microscopic and the macroscopic in ways that were once unimaginable. But the future of quantum weave research isn't just about technology, it's about collaboration. Breakthroughs in this field require the combined efforts of physicists, engineers, computer scientists, and even philosophers, all working together to unravel the mysteries of the universe. International projects like the Large Hadron Collider and the Square Kilometre Array Telescope are perfect examples of what can be achieved when we pool our resources and expertise. These collaborations don't just advance science, they remind us that the pursuit of knowledge is a shared human endeavor, one that transcends borders and disciplines. As we look ahead, it's clear that the quantum weave holds the potential to solve some of humanity's greatest challenges. From climate change to energy sustainability, the insights we gain from quantum research could pave the way for transformative solutions. Imagine quantum sensors that detect environmental changes with unparalleled precision, or quantum-inspired algorithms that optimize renewable energy systems. The possibilities are as vast as the cosmos itself, and they remind us that the quantum weave isn't just a scientific concept, it's a tool for shaping a better future. But the journey doesn't end here. The quantum weave invites us to dream bigger, to ask questions we've never dared to ask before. What other secrets does it hold? How might it change the way we see ourselves and our place in the universe? These are the questions that drive us forward, guiding our exploration of the cosmos and the quantum realm. And as we continue to probe its mysteries, we're not just uncovering the secrets of the universe, we're discovering the threads that connect us all. What if the key to solving humanity's greatest challenges lies not in the vastness of space, but in the intricate patterns of the quantum weave? From energy crises to climate change, the quantum realm holds untapped potential to revolutionize how we live, work, and thrive on this planet. Imagine a world where quantum technologies unlock new ways to harness energy, monitor our environment, and even predict natural disasters before they strike. This isn't science fiction, it's the promise of the quantum weave, a framework that connects the smallest particles to the largest global challenges we face today. Take energy, for example. The quest for sustainable power sources is one of the most pressing issues of our time, and quantum mechanics might hold the answer. Quantum computing could revolutionize energy storage by simulating new materials with unprecedented efficiency. Picture batteries that charge in seconds and last for days, or solar panels that capture sunlight far more effectively than anything we have today. These breakthroughs could transform how we power our homes, cities, and transportation systems, reducing our reliance on fossil fuels and helping to combat climate change. The quantum weave isn't just a scientific curiosity, it's a toolkit for building a cleaner, greener future. But the potential of the quantum weave goes beyond energy. Quantum sensors, for instance, are already showing incredible promise in environmental monitoring. These devices, which exploit the extreme sensitivity of quantum states, can detect minute changes in temperature, pressure, or magnetic fields. Imagine deploying quantum sensors across vulnerable ecosystems to track deforestation, monitor ocean health, or even predict earthquakes with unparalleled precision. By giving us a clearer picture of our planet's delicate balance, these technologies could help us make smarter, more sustainable decisions. Climate change, in particular, stands to benefit from quantum advancements. Accurate climate modeling requires processing vast amounts of data, a task that classical computers struggle with due to their limitations. Quantum computers, on the other hand, could handle these complex calculations with ease, enabling more accurate predictions about weather patterns, sea level rise, and the long-term impacts of global warming. This isn't just about understanding the problem, it's about empowering policymakers, scientists, and communities to take meaningful action. The power of the quantum weave doesn't stop at practical applications. It also lies in its ability to inspire collaboration across disciplines. Solving global challenges requires more than just physicists. It demands the combined efforts of engineers, biologists, computer scientists, and even social scientists. Interdisciplinary research is the backbone of quantum innovation, breaking down silos and fostering creative solutions to complex problems. When experts from diverse fields come together, the quantum weave becomes more than just a scientific framework. It becomes a shared vision for a better future. As we explore the quantum weave's potential to address humanity's challenges, it's clear that this framework isn't just about understanding the universe, it's about shaping it. From renewable energy to climate resilience, quantum technologies offer a glimpse of what's possible when we harness the power of the smallest particles to tackle the biggest problems. And as we continue to push the boundaries of what we know, the quantum weave might just inspire a new era of exploration and discovery, one where humanity not only survives but thrives in harmony with the cosmos. But what does this mean for the future of exploration? How might the quantum weave guide us as we venture beyond Earth, into the stars and beyond? That's where our journey takes us next. As we stand on the brink of a new era of space exploration, the quantum weave offers more than just a framework for understanding the cosmos. It could be the key that unlocks the next chapter of human discovery. Picture this: missions designed not just to explore planets and stars, but to probe the very fabric of reality itself, unraveling the mysteries of black holes, wormholes, and the quantum forces that shape them. This isn't the stuff of science fiction. It's the future of scientific inquiry, where the quantum weave becomes both our guide and our destination. Consider the Voyager probes, humanity's first emissaries to the outer reaches of our solar system. Launched in the 1970s, these spacecraft have traveled billions of miles, sending back data that transformed our understanding of planets like Jupiter and Saturn. But what if the next generation of probes could go even further, not just in distance, but in scope? Imagine spacecraft equipped with quantum sensors, capable of detecting the faint ripples of spacetime or the subtle signatures of entangled particles. These missions wouldn't just explore the cosmos, they'd delve into the quantum weave itself, revealing how the universe operates on its most fundamental level. The Artemis program, NASA's ambitious plan to return humans to the moon, offers another glimpse into this quantum-inspired future. While its primary goal is to establish a sustainable presence on the lunar surface, the technologies developed for Artemis could also pave the way for deeper exploration. Quantum communication systems, for instance, could enable instantaneous data transfer between Earth and distant spacecraft, revolutionizing how we conduct missions in deep space. And as we venture further, the quantum weave could provide new tools for navigation, energy generation, and even the discovery of resources hidden in the cosmic void. But the quantum weave's potential goes beyond practical applications. It could redefine what it means to explore. Take black holes, for example. These enigmatic objects, where gravity is so strong that not even light can escape, are some of the most extreme environments in the universe. Yet they are also windows into the quantum realm, where the rules of general relativity and quantum mechanics collide. Future missions might use quantum sensors to study the event horizons of black holes, shedding light on phenomena like Hawking radiation and the information paradox. These discoveries wouldn't just deepen our understanding of black holes, they could reveal how the quantum weave operates under the most extreme conditions. Wormholes, too, offer tantalizing possibilities. These hypothetical tunnels through spacetime, predicted by the equations of general relativity, could provide shortcuts across the cosmos, if they exist. While we haven't yet observed a wormhole, the quantum weave might hold clues to their formation and stability. Imagine a future where spacecraft equipped with quantum instruments search for the faint signatures of wormholes, opening up new pathways for exploration. These missions wouldn't just push the boundaries of science, they'd challenge our very notions of space and time, revealing a universe far more interconnected than we ever imagined. As we look to the stars, it's clear that the quantum weave isn't just a scientific concept, it's a call to action. It inspires us to dream bigger, to ask questions we've never dared to ask before, and to see the universe not as a collection of separate objects, but as a unified whole. From the Voyager probes to the Artemis program, humanity's drive to explore has always been fueled by curiosity and a desire to understand our place in the cosmos. The quantum weave invites us to take that journey one step further, to explore not just the universe, but the very fabric that binds it together. And as we venture into this new era of exploration, we're not just uncovering the secrets of the cosmos, we're also grappling with questions that go beyond science. What is the ultimate purpose of the universe? Are we alone in this vast expanse, or is the quantum weave a sign of something greater, a cosmic design that connects all things? These are the questions that drive us forward, guiding our exploration of the quantum realm and the stars beyond. The quantum weave isn't just a tool for understanding the universe, it's a mirror reflecting back to us the mysteries of existence itself. And as we continue to probe its depths, we might just find that the answers lie not in the stars, but in the threads that connect them. What if the universe isn't just a random collection of stars, planets, and particles, but something far more profound, a grand design woven together by the threads of the quantum weave? This isn't just a scientific question, it's a philosophical one that touches on the very essence of existence. Through the lens of the quantum weave, we can begin to explore the universe's purpose, not as a static question with a single answer, but as a dynamic, ever-evolving inquiry into the nature of reality itself. Think of the universe as a cosmic symphony, where every particle, every star, every galaxy plays its part in a vast, interconnected melody. Just as a symphony relies on the harmony of countless instruments, the universe depends on the intricate interplay of quantum forces. From the tiniest quarks to the largest galaxy clusters, everything is connected, each thread of the quantum weave contributing to the overall composition. This idea of harmony isn't just poetic, it's rooted in the mathematical elegance of the quantum realm, where particles and forces follow precise, interwoven rules. But what does this interconnectedness say about the universe's purpose? For some, it suggests a deeper meaning, a sense of unity that transcends the chaos of everyday life. If everything is connected, then every action, no matter how small, has the potential to ripple through the cosmic tapestry, influencing the whole. This perspective invites us to see ourselves not as isolated beings, but as active participants in the universe's unfolding story. It's a vision that bridges science and spirituality, offering a way to find meaning in the vastness of existence. Of course, not everyone sees the quantum weave as proof of a grand design. Some argue that the universe's interconnectedness is simply a natural consequence of physical laws without any inherent purpose. Yet, even this view sparks wonder. The idea that complexity and beauty can emerge from simple, fundamental principles. Whether you see the quantum weave as evidence of a cosmic plan or as a testament to the power of natural laws, one thing is clear: it inspires a deep sense of curiosity about the universe and our place within it. This sense of wonder is perhaps the greatest gift of the quantum weave. It challenges us to look beyond the surface, to question our assumptions, and to embrace the mysteries that lie at the heart of existence. It reminds us that the universe is not just something to be studied, but something to be experienced, a living, breathing system that we are part of. And as we continue to explore its mysteries, we're not just uncovering the secrets of the cosmos, we're discovering new ways to see ourselves and the world around us. As we reflect on the universe's purpose through the lens of the quantum weave, it's clear that this framework offers more than just answers. It invites us to ask deeper questions. What does it mean to be part of a universe where everything is connected? How can we live in harmony with the cosmic symphony? These are the questions that drive us forward, guiding our exploration of the quantum realm and beyond. And as we wrap up this journey, it's time to look back at the key insights we've uncovered, bringing together the threads of the quantum weave into a cohesive vision of the cosmos. As we bring this journey through the quantum weave to a close, let's take a moment to reflect on the incredible tapestry of ideas we've explored together. We began by unraveling the origins of the quantum weave, tracing its roots back to the early days of quantum mechanics, where pioneers like Max Planck and Albert Einstein first glimpsed the strange, counterintuitive nature of the subatomic world. From there, we ventured deeper, discovering how this intricate framework connects the smallest particles to the grandest cosmic structures, revealing a universe that's far more interconnected than we ever imagined. We delved into the mysteries of entanglement, where particles separated by vast distances remain intimately linked, defying our classical understanding of space and time. We explored how quantum fluctuations in the early universe seeded the formation of galaxies, and how dark matter and dark energy, those enigmatic forces shaping the cosmos, might be woven into the same cosmic fabric. From black holes to wormholes, we saw how the quantum weave challenges our notions of reality, offering glimpses into dimensions and possibilities that stretch the limits of our imagination. But the quantum weave isn't just a scientific concept, it's a lens through which we can explore the profound questions of existence. It invites us to rethink our place in the universe, not as isolated observers, but as active participants in a dynamic, ever-evolving cosmic dance. Whether we're contemplating the origins of life, the mysteries of consciousness, or the future of space exploration, the quantum weave reminds us that we're part of something infinitely greater than ourselves. As we look to the future, the quantum weave holds the promise of transformative breakthroughs, from quantum computing and energy technologies to new ways of exploring the cosmos. It challenges us to dream bigger, to ask bolder questions, and to embrace the unknown with curiosity and courage. But with this potential comes responsibility. As we continue to unravel the threads of the quantum weave, we must do so with humility and care, ensuring that our discoveries are guided by ethics and a deep respect for the interconnectedness of all things. Before we wrap up, I want to leave you with a thought that captures the essence of the quantum weave. In this vast, interconnected cosmos, we are not just observers, we are threads in a cosmic tapestry, each one essential to the beauty and complexity of the whole. Whether you're a seasoned science enthusiast or someone just beginning to explore these ideas, I hope this journey has inspired you to see the universe and your place within it in a new light. Now it's your turn. What excites you most about the quantum weave? How do you see these ideas shaping the future of science, technology, or even philosophy? Share your thoughts in the comments below. I'd love to hear your perspective. And if you enjoyed this exploration, don't forget to like, subscribe, and hit that notification bell so you never miss a journey into the mysteries of the cosmos. Thank you for joining me on this adventure through the quantum weave. Until next time, keep asking questions, keep exploring, and remember, in the quantum weave, we are all connected, part of a cosmic dance that spans the smallest particles to the largest galaxies.